কি এদিকের বাজার বেশ খারাপ যে? খালি অফিসে কি দেখতে পাচ্ছি সুচরিতা?
স্যার আপনাকে পিন করব?
হ্যাঁ করো না, এগুলো এখন আছে না ওবিএস এ? আচ্ছা So Amarto is here. Amarto, first speaker is Amarto. Then Moloy. Moloy, are you here?
Yes, sir, I am present.
So could you please try sharing your screen?
Okay, sir. Okay, sir, can I start now or?
No. Just practice.
Okay, sir.
Yes, great. Okay.
It is visible, sir?
Yeah, it's perfect.
Okay, this is my presentation.
Yeah, Austin. Yeah, please stop sharing and let others.
Okay, sir. Thank you, sir.
Austin, are you here? Would you like to share your screen? Austin, we can't hear you.
Hello, Amy.
Austin, would you like to share your screen? Dr. Negi, are you here?
Sir, this is Austin D'Souza. Shall I start sharing, sir?
Yeah, please. Yeah. Yeah, great. It's working fine. Thank you.
Yes, sir.
Faham Shahid, are you here?
Yes, I can hear, sir.
Okay, thank you. So could you please stop sharing? Yeah. Let's others have a
Yes,
practice. Just we have 5 minutes more.
Yes.
Fahim Shahid?
Yes, sir, I'm here, sir. Should I share the
Yeah,
screen?
please.
Is it okay,
Yeah.
sir?
Yes, great. Okay. So, Dr. Negi, would you like to share your screen, please?
Yes, sir. Hello. Am I audible, sir?
Yeah, you are audible. Yeah.
Yes. Sir, it is sharing, sir?
Yes.
Yes.
Yeah. So your presentation is not yet there. Would you?
Yes, sir. I should unshare.
Yeah, it's fine, no problem. So I think at that time it will work certainly. Dr. Boshak, would you like to share? Dr. Boshak, are you there? Yes. Okay, great. Yes, the screens are being shared. Yeah, fine, perfect. Okay. Sushanto Mondo, are you here? Dr.
Yes,
only?
I am sharing. I am sharing.
Okay. So, Dr. Basha, could you please stop sharing? Yeah, thank you. Please stop sharing. Yeah, great.
Okay.
Coming. Thank you. Ashik Hushan Mirza, would you please share? Ashik Hushan Mirza, are you here? I cannot find his name. Okay. Maybe Taposh Haldar, are you here? Taposh Haldar, not yet joined. Sharabjit Kaur, are you here? Sharabjit? Okay, I can see chairperson has already joined us. Yeah, 2 more minutes. So anyone who left wants to share your screen? I guess we have checked with all those who are present till now. Okay, so looks great. Yes, very good morning to Professor Detrich. I think it's still morning, right? At
Good
your
morning,
place?
good morning. Yeah, it's 12 o'clock
12 o'clock.
here. So it's no problem. Okay, I will follow this with passive also, and then I'm with you.
Okay, sure.
So, it starts in some minutes now.
Yes, in 1 minute.
Yeah, okay, that wasn't time. Okay, good luck in the session.
Okay,
And
yeah.
yeah, see you later.
See you. Okay. So good morning, good afternoon, and good evening to you all, ladies and gentlemen. So welcome you back to the third day, the final day of this 3-day 15th International Conference, MAST 2021. So today, this is the first technical session 7A. Technical session 7B is also going parallel. So I hope that no participants from 7B is here. If somebody is from 7B is here, please have a look at your email. I have already sent you the link to go to 7B. Hope nobody is here for 7B. So for 7A participants, we have 10 speakers. And without any further delay, may I request our session chair, Dr. Moitri Shen, to chair this session. Madam, the session is yours.
Thank you. Am I audible to everyone?
Yes, audible. Yeah.
Thank you, first of all, for inviting me to chair the session. And I hope this conference, already it is a great success, and it will continue to be. So without further ado, I think we can start the first presentation, right? You can call Shudhanshu. Who will present, Shudhanshu or Amarto?
I think till now they haven't joined yet.
Okay.
Okay. So due time, maybe they are going to join. So the board marked are the speakers. So the next
So Amarto, I think, will be the
speaker, but I think he has not yet joined.
Okay. So let us wait for a few
No,
minutes.
maybe we can go to the next speaker. Yes.
Okay, fine. So, the next speaker, Molay Kumar Ruidas, are you here?
Yes, ma'am, I am present.
Yeah. So the next, the talk will be on NDPOPP, a natural discrete version of one parameter polynomial exponential distribution, by Molay Kumar Ruidas. Please, Molay, you can share your screen and start your presentation.
Okay, ma'am. I think it is visible.
Yeah, it is absolutely visible.
Thank you,
can
ma'am.
make it full screen also if you want.
Okay, wait.
चलिए ना क्या
Okay, ma'am.
Right, yeah.
Now it is clear, I think.
It is clear now.
Okay, ma'am. Thank you, ma'am.
Yeah.
Good evening, everyone. Myself, Malay Kumar Ruidas, from Department of Statistics, Triveni Devi Bharatiya College, from Raniganj. First of all, I want to thank Professor Abhishek Odhikari, who has given me this opportunity to present this paper in this 15th virtual conference, international virtual conference. Thank you, sir. So so let's start quick. Today my topic is about NDOPPE, a natural discrete version of one parameter polynomial exponential distribution. We are the three authors. You can see Sudhanshu S. Maiti, myself, and Suman Taddu. Okay, these are the contents of my paper. First, introduction. I have used the paper. Then motivation, where I get motivated. I have derived the structural and reliability properties of the proposed distribution. Then there is a parameter which are estimated by MLE. Then the application, the real life application I have shown. Then comes table, and then conclusion. Finally, the conclusion. Okay, what is introduction? What are the introduction? You all know that there are many standard discrete distribution. We all heard about the binomial, Poisson, geometric, negative binomial. These are the model lifetime data, but these models are too restrictive. For example, we know for the Poisson distribution, the mean and variance is same. So it is not appropriate as it imposes the restriction of equidispersion. Similarly, for binomial distribution, we know that the mean is greater than variance, so it imposes the restriction of underdispersion. As a consequence, various model has been prescribed. There are two methods, two approaches. One is discrete concentration, and another is discrete analog approaches. By this method, we can draw less restrictive model. Next, motivation. Where I get motivated? There are a number of restrictive, less restrictive discrete distribution, but still there are some room for constructing flexible discrete distribution. Here I have proposed the distribution which is appropriate for underdispersion, overdispersion, and equidispersion types of data, discrete data. Okay, so Bouchard and Jagdawdi, two eminent statisticians, they in 2018 has proposed the continuous distribution and named one parameter exponential distribution, which is the unified approach in generalizing the linear distribution. We all heard about linear distribution. So, and now Bouchard and Jagdawdi, they propose the continuous distribution. Here in this paper, we, with three authors, propose the discrete distribution. So this is a form of my discrete distribution. A random variable is x is said to have a natural discrete one parameter polynomial exponential distribution with success probability theta. Here, this is the structure of my PMF. If you look clearly that this is the weight. Here, it is the PMF of negative binomial distribution with weight. Here, success k plus 1 success, and the success probability is theta, and ak are the non-negative constant, and r is the positive integer. This is the form of my distribution. Next, we have plotted the distribution. Here you can see that as the number of trials increases, the probability is decreasing. For the first figure, you see that it is for the defined values of r, and for the second figure, you see that it is for the defined values of theta. For NDOP distribution, we derived some property. Basically, for any type of distribution, we derive the structural properties. Here, the structural properties like moment generating function, probability generating function, mth factorial moment. These are the form of the moment generating function, probability generating function. Okay. Next, the first and second order raw moments. These are the raw moments. One can easily find out the mean and variance of this distribution. from the mean and variance. These are the property of a particular distribution, and here the raw moments are the properties of my NDOPP distribution. Now the reliability properties. There are some other properties like reliability properties. This is the form of the reliable properties. The first is the reliability function, the second is the failure rate function, and the third one is the mean residual lifetime. What is reliability function? Reliability function is the probability of an item operating for a certain amount of time without failure. This is the form. And the failure rate function represents the probability of failure per unit time, given that the component has already survived to time t. This is the definition of the said reliable properties. Similarly, the mean residual lifetime is the expected additional lifetime given a component has survived until time t. I have drawn some result. If ID, here ID stands for index of dispersion, its formula is variance by mean. For a particular distribution, if ID greater than equal to 1, the distribution is over dispersed. Here, for my NDOPP distribution, ID decreases monotonically in theta. As theta tends to 1, ID also tends to 1, and ID tends to infinity as theta tends to 0. So, the NDOPP distribution can be used for the count data analysis with overdispersion. For the NDOPP distribution, we know there are different types of method for estimating the parameter. Here, for my NDOPP distribution, the method of moment and the method of MLE for the parameter theta are same. Okay, so we can find any one of the method, and it can be obtained by solving this nonlinear equation. Here is the nonlinear equation, and we have gone through the name that since the PMA belongs to one parameter exponential family, here x bar is the UMB of this nonlinear equation, but exclusively the MVU of theta is not available. MVU means minimum variance unbiased estimator. Okay, simulation study. What is simulation study? Simulation study means we generate the random variables from the particular distribution. Generating random variable is known as simulation study. Okay, so Poisson distribution, negative binomial, these are the standard distribution. There is a code, there is a proper proforma for generating random variable. But for my new NDOPP distribution, this is the following algorithm by how we can generate the random variable from NDOPP distribution. First, we have to draw a random variable from uniform distribution, and we denoted this as UI. Second, if UI lies between these two particular value, then we take we draw the random variable from negative binomial, and if UI less than this particular value, you can see, then we draw random variable from geometric distribution. This is the procedure for generating random variable. Now, after generating random variable, a simulation study is carried out with 1000 repetition. Here we choose the constant I have said earlier, that A0, A1 are the non-negative constants. So here we take A0 is equal to 1 and A1 is equal to 1, and taking theta is equal to 0.4. Two measures are computed using the R software. We all heard about the R software. Bias and mean square error. These are the two measures I have calculated using the software. This is the formula for bias. Sorry. Next, I have plotted the bias and MSE, which I have obtained in the programming language. Here you can see that both the bias and MSE decreases as the sample size increases. So for MLE, it tends to 0 for large n, which indicates the accuracy of my MLE, which indicates the accuracy of my distribution MLE. And MSE, for MSE, it approaches to 0, which indicates that the estimate we obtain is consistent. Here we know that consistent is one of the property of a good estimator. Next, okay. I have applied my distribution to 8 datasets. The dataset I have taken from Wilmot 1987, 4 data from Wilmot 1987, 2 from Bermudez, and remaining 2 from Bolchard et al. I have compared my distribution with this standard distribution, Poisson negative binomial discrete X gamma. Okay. We have then shown the fitted probability for each dataset, and comparison have been made in terms of log likelihood, also as well as observed chi-square statistic. This is a table. You can see that here the data set is the Wilmot automobile insurance claim data. Here the number of claims for each policy and the corresponding observed frequency is given in the first 2 columns. Okay, number of claim and observed frequency. And in the right hand column, you can see that my NDOBP is fitted using taking A0 and A1 is equal to 1. You can observe that negative log likelihood value is less than the other distribution on the below right side, and observed chi-square value is 57. Now I have result. The result I have drawn from this table, that the expected frequency for NDOB distribution is very very near with the observed frequency, and the observed chi-square value and the negative log likelihood value for the NDOB distribution is less. You can see from the table that for my distribution, the chi-square and negative log likelihood value is very small, which is a good criteria for a particular distribution. This is since there is only one parameter theta here in my distribution, only one parameter, so it is sufficient to select the model with respect to negative log likelihood. Now conclusion. Finally, what I have drawn that my NDOBP distribution has better performance than the other model, and the dispersed data can be fitted more flexibility using NDOBP model than any other model. Okay, these are the reference I have used. This reference. And thank you. This I hand here.
Okay. Thank you to the speaker. And now, if anyone have any question, you can ask. You can have 2-3 minutes for the questions. And before the next presentation, I would like to just announce that every speaker will have around 12 minutes, and including the question answer session and everything. So please try to complete it within that time, everyone. So yes, if audience have anyone of the audience have any question, please ask.
I have a question. Hello, am I audible? Hello.
Hello. Yes. Yeah, you are, but your voice is very low. Can you please raise your voice or?
Hello.
Yeah.
How many
You are audible, but it's very low. You are sounding. Your voice is very low.
Okay. How many parameters have you used?
Here I have only used one parameter. You can see from the title that it is the version of one parameter polynomial exponential. Here I have used only one parameter.
Okay.
Any more question? Or shall I stop sharing?
Anyone have any questions? Or if not, we can thank the speaker and you can stop the presentation. And thank you for nice presentation.
Thank you, ma'am. Okay, I am stop sharing.
Okay. So the next person is Austin Marvin D'Souza from Karnataka. Are you here?
Yes, ma'am. Yes, ma'am.
Yeah. So the speaker will be speaking on relation between general Randic coindex and general sum connectivity coindex. So Austin, you can start your presentation, please. And you'll have 12 minutes, including the question and answer anything, the audience, everything. So please try to maintain. Thanks.
Ma'am, are you able to see the screen?
Yes, it is visible and you are audible also perfectly.
Yes, ma'am. I'm Austin Mervyn D'Souza from Department of Mathematics from Ranichanam University, Belgavi, Karnataka. The title of my paper is Relation between the General Randic Coindex and General Sum Connectivity Coindex. So throughout this paper, I'll be mainly dealing with initially the definitions of these two families of indices, and later on the relation between these two families, how they are related, or the inequalities between them for certain family of graphs. Introduction. So here, in 1998, the General Randic Index was defined, and it was defined as Rk of G equal to summation of du into dv to the whole power k, where du is actually the degree of the vertex u and dv is the degree of vertex v. This summation actually runs over all the vertices which are adjacent to each other in the graph G. The graph G could be any molecular graph in general. Now this k is actually any real number. It could we could write k could be any real number like 1, 2, 3, or -1 or -2, any real number. So this is actually the General Randic Index. Next, in 2008, the first the first coindex was defined. It was actually the first Zabrak coindex, and it is not a general index, and it was defined as summation of du plus dv, where the summation ran over all the edges which were not all the vertices which are not adjacent to each other. Now in 2020, the General Zabrak coindex was defined. It was also called as the General Zeroth Order Randic coindex, but it could also be called as the General Zagreb coindex. It was defined as a summation of du to the power k minus 1 plus dk dv to the power k minus 1. This is the history about the General Randic Index and the coindex. But what we have defined in this paper is the General Randic Coindex, taking inspiration from all the developments that took place initially. And we have defined this index, that is, it is a summation of du into dv to the whole power k, where u and v are not adjacent to each other. So that means it is not a uv is not a edge in the vertex in the graph G. Now these are the 6 variants I've listed here, which are the not that only these are the 6 variants we have under a General Randic coindex. We can have infinitely many variants, but for my study here throughout this paper, I'll be dealing with only 6 variants. So one can always take any number of variants. On the other hand, we have another family, that is the General Sum Connectivity Coindex. But this index, what we have here, is the General Sum Connectivity Index, not the coindex. It was defined in 2010, and it was defined as the summation of du plus dv to the whole power k, where u and uv is an edge in the graph G. Taking inspiration from this particular index, we have defined the new index as the General Sum Connectivity Coindex. We have defined the General Sum Connectivity Coindex, where the only difference that we can see here is uv is not an edge actually in the graph G, and it is denoted with the bar here. That's the only difference. Every coindex is denoted with the bar. The index is without the bar here. And here are the few variants of the General Sum Connectivity Coindex. Here there are 3, and the other 3 I have listed here. We could see actually few references here, which are the co-indices. All people before me also people have defined, but what we see is the particular co-indices, not the general family itself. And here is the table which actually gives us the correlation coefficient between the two families of indices. The vertically I have represented the general Randic co-indices, and horizontally I have listed the general sum connectivity co-indices. And the correlation coefficient, as you see here throughout, maybe the last two rows do not show very good correlation. Rest of them all show very good correlation. The values are very close to either 1 or -1. As you see here, this is almost equal to 1. And diagonally, when we see it is almost 0.99, most of the values, except for maybe 2. So they have, these two families have very good correlation coefficient. They are very much related. And therefore, we will be, in this paper, we'll be discussing about few relations or the inequalities, how they are related for different families of graphs. So before I go into the first theorem, here are the two lemmas which I will be using. I have not given these the proofs here. The proofs I have actually, these lemmas have taken it from other paper of mine. And what do these lemmas say? The first, basically in both these lemmas, I have defined two functions, r of x comma y is equal to x into y to the whole power k, and s of x comma y is equal to x plus y to the whole power k. Both are functions defined for all x comma y belonging to n, where k could be any natural number. So these are the three relations we get between these two functions. So there are three relations here for different values of k. Similarly, we have the other lemma also. Slightly differently, the functions have been defined here in this case, r and s. And similarly, we have got three different relations, the inequalities we have. These lemmas I'll be using. Here is the first lemma. Do we actually, before I begin this theorem, do we have any similar results in the mathematics literature? Yes, we have actually one or two results I have come across. What is that result? It is actually the inequality between the Randic index and the sum connectivity index. So it was the index, not the co-index. Secondly, it was the particular index, not the general family itself. So there we see the inequalities are there for path graphs as well as for any graph without pendant vertices. But here in this paper, what I have done is for different family of graphs I have taken, not only path graph, I have taken for some star graph, complete graph, regular graph, all those things. And also not just the particular indices, rather I have taken the family of indices itself. So here in the first theorem, what we have is, for all path graphs where n is greater than 2, the inequality between the general sum connectivity co-index and the general Randic co-index is given as shown here. We have got two cases for k greater than 0 and k less than 0. There are two different cases. Here is the proof actually. The proof is very simple. By using the lemmas I have done it, one can go through this. I will not explain the theorem due to the time constraint. So the methodology with which I have proved it is very simple. Anybody could easily understand it. So there are two cases to prove the whole theorem. So here there are 6 corollaries which follow the theorem just by replacing the value of k is equal to 2, 1, half, -1, and -2. 6 different values I have taken, and we have 6 different corollaries here. So these happen to be the particular cases of the previous theorem. The next theorem is about the relation between the inequalities between the general sum connectivity co-index and general Randic co-index for all star graphs where n varies. N is nothing but the number of vertices should be greater than 2. Here also we have got two cases where k greater than 0 and for k less than 0. And here there are 6 corollaries which follow from the theorem by replacing the value of k equal to 6 different values, as I told earlier, that is 2, 1, half, -1, and -2. So here are the 3, and the remaining 3 are here. The third theorem is about the inequality between the sum connectivity co-index and general Randic co-index for all R regular graphs, where R is the degree of every vertex in the graph. N must be greater than or equal to 4, and R is the degree of every vertex must be greater than or equal to 1. But only one condition here is that the graph should not be a complete graph, because every complete graph is also a regular graph. But here in this case, it shouldn't be a complete graph. Then the following inequalities hold, and we have got 6 different cases: 3 for k greater than 0 and 3 for k less than 0, and also we have got for different values of R, we have 6 different cases. And of course, we have got next 6 corollaries which follow from the third theorem. The fourth theorem is about the inequality between these two families of indices for all complete bipartite graphs. Complete bipartite graphs, here we have got 4 cases: 2 for k greater than 0 and 2 for k less than 0, and of course for different values of m and n, where m and n are 2 sets of is the number of 2 sets of vertices. So the next, also we have 6 corollaries listed here for different values of k. The fifth theorem is the inequality between the two families of indices for all connected graphs. For any connected graph, this is one of the most general theorem we have, but here only condition is that it shouldn't have any pendant vertices. Otherwise, this is one of the most general theorem we have. But the moment we have, let's say, path graph or star graph or bipartite graph, in all these cases we'll have at least we might have pendant vertices. Therefore, in this case, it covers most of the graphs, I could say, but except those that do not have pendant vertices. So here we have got 2 cases for k greater than 0 and k less than 0. In this case, the general sum connectivity index of any connected graph is less than or equal to general Randic coindex, and whenever k is greater than 0, and otherwise whenever k is less than 0, we have case. So there are 6 corollaries we listed here. The next theorem is, the next 4 theorems, in fact, I have not given the proofs here. The proofs are very simple. What I have done here is to express the general sum connectivity coindex in terms of the general Randic coindex, and also that is for k greater than 0, and for k less than 0, I have expressed general Randic coindex in terms of general sum connectivity index for all path graphs where n is greater than 2. And the next 3, we have similar ones. So we are trying to express one particular family of indices in terms of the other family of indices. Here also the general Randic coindex is expressed in terms of the general sum connectivity coindex. So this is for this all star graphs where n is greater than 2. The previous one was for all path graphs. Next similar theorems we have here. This is for regular graph. One is for regular graphs, the other one is for complete bipartite graphs. Here also I've done the same thing, trying to express one particular family of indices in terms of the other family of indices, co-indices, sorry. And the last 2 are actually the inequalities for graphene structure, 2D structure of graphene, and N-naphthalenic nanotube structure. We have similar relations, inequalities. And in fact, for any these theorems could also be extended for any kind of nanotubes that we have, and it could be easily proved. Yes. So the conclusion, basically we have obtained a few the inequalities between the 2 family of indices, and also we have extended these inequalities for particular cases of 6 different variants of these families. And these results can also be applied on the nanotubes listed here, or many more nanotubes that we have, we can extend it. These are the few references that I have used for my paper. Yes. Any questions?
Yes, if anyone have any questions, please you can ask the speaker, and I'll humbly request everyone to please restrict your talk within maybe 11 to 12 minutes, please. So if anyone has any question, please you can ask other people. Or otherwise, we can thank him and invite the next one.
Shall I end it, ma'am?
Yeah, if anyone doesn't have any question, you can stop sharing and we can go.
Thank you, ma'am. Thank you for the opportunity.
to presentation. So the next person is Mrinmoy Shodhar. Are you here?
So Mrinmoy has been shifted to the next session. So
Okay, yes. I'm sorry. So, Mr. Anil Negi, are you here?
I'm here. Yes, sir.
Yes. So Anil will be speaking on mathematical analysis of dynamic behavior of an irregular, initially stressed piezomagnetic material substrate impacted by a moving line load. So Anil, please, you can share your screen and start your presentation. And please,
Is my PPT visible?
yeah, your PPT is visible.
Okay.
Yeah, please try to complete it by
Yes, ma'am.
maybe 4:45. Thanks.
Very good evening to all of you. And I am Dr. Anil Negi from VITF University. And I'm going to present one of my research work entitled Mathematical Analysis on Dynamic Behavior of an Irregular Initially Stressed Piezomagnetic Material Substrate Impacted by a Moving Line Load. So first of all, just I'm giving a brief introduction regarding piezomagnetic materials. So there are some antiferromagnetic crystals which can be characterized by a linear coupling between magnetic polarization and magnetic strain. This type of materials are called piezomagnetic material structures. Here, just due to this, some mechanical strain, the magnetic induction can be take place inside the structures. Therefore, these materials are called piezomagnetic materials. So there are some special kind of magnetostrictive materials which are now used in the energy harvesting. Energy. These type of materials are very much used. Where the ground vibrations are stored, and due to the magnetic inductions, we can convert them into optical energy. So here, just as I discussed there, this mechanical stress results in this spontaneous magnetic movement here. It is just basically the linear mechanical effect. Means if they apply any mechanical strain or stress, then magnetism generated inside the structure, or due to the generation of magnetic, it also works vice versa. Due to the induced magnetic movement, we can see the mechanical strain inside the structure. It is just analogous to the linear electromechanical effect in piezoelectric materials. So this is the geometry of the problem. Here we have I have considered the line load F moving with the uniform velocity v on the rough upper surface of piezomagnetic material substrate. The Cartesian coordinate is selected in such a way that x-axis representing the direction in which the line load moves, and z-axis pointing vertically downwards. Here, an irregularity of maximum depth h and span 2b has been considered on the upper surface, and this irregularity on the upper surface can be due to weathering and erosion phenomena, or it can be nowadays artificial irregularity also are also generated on the upper surface due to some design requirements during the manufacturing process. So a line load is moving, it is considered it is moving with velocity v on the upper surface here. Now, the equation of the upper surface containing irregularity represented by equation 1, in which Lx is associated with the shape of the irregularity. And here we can see that it is here, it is totally dependent upon here. If we take 2b here, b square 1 minus x square upon b square, it totally depend upon here. So if it is x upon b equal to 0, it is represented the rectangular shape irregularity. If it is x upon b lies between 0 to 1, it is represented as the parabolic shape irregularity. And here I will also we will also discuss the case where x upon b equal to 1 when there is no irregularity on the upper surface. And here epsilon is the ratio of the maximum depth. Equation 2 and 3 represents the equation of motions for functionally graded piezo-magnetic metal substrate. Now, the stress strain relation for functionally graded piezo-magnetic metal substrate can be represented by equation 4, in whichCij's are elastic constant, Hij's are piezo-magnetic constant, mu ij are magnetic permeability, and others are Eij's are strain constant, and mi's are the component of magnetic intensity. Now, the stress strain component, the relation between mechanical displacement and strain component, as well as the relation between magnetic intensity and magnetic potential, can be represented through equation 5, in which 5 the magnetic potentials. Now, here we have just applying the plane strain deformation condition. Here we have considered that the width of the structure is very, very large as compared to the particular cross sections, the dimension of particular cross sections. Therefore, the strain along the width can be 0. So therefore, we apply the plane strain deformation condition in the form of equation 6. Now, see, again, in the realistic situation, the material may not be homogeneous, maybe some heterogeneity may be there. So therefore, we have considered functionally graded materials. Functionally graded means the material properties are dependent upon the position variable, and it is just like the heterogeneity at a microscopic level. We can consider where mu is the parameter of functionally gradedness. Now, with the help of equation 5, 6, and 7, in equation 2 and 3, and just apply that functional gradedness property, we can obtain equation 8 to 10. These are the boundary condition for to solve the problem. At the upper surface, we have considered equation 11 and 12. It is represented that the upper surface is the traction of the upper surface. Okay, when any load is applying here, the traction of the upper surface here, and it is represented in terms of Dirac delta function here. And this is the equation 13 represents magnetically short conditions. That means the magnetic flux distributed over the upper surface is 0. And equation 14 represents the condition for magnetically open conditions. That means the magnetic potential difference is 0. So for the magnetically short condition, we can use equation 11, 12, and 13. And for magnetically short open condition, we can use equation 11, 12, and 14. So the solution, it is just type of semi-inverse type of problem. Here, just we can say, consider maybe the solution may be considered in the form of equation 15 and 17. Now, I have just reduced this problem is very lengthy, so I just reduced the problem by skipping some steps due to some time, just by in view of the time constraint here. So equation with the help of equation, all the obtained equations, we can get an algebraic equation in terms of Q, means a biquadratic equation we can get, which can give us the two roots Q1 and Q2. And in view of this, equation 15 to 17 can be represented in this form of equation 18 to 22. Now, again, since the upper surface is irregular, so irregularity is there. Therefore, the arbitrary constant involved in the solution part, it can be represented in terms of the perturbation parameter here. And it is indicated through equation 21. Again, if we are while considering the equations 18 to 20 and the approximation used for the upper surface in the boundary conditions 11 to 30, we can get the induced incremental stress and magnetic potential function for magnetically short case as in the form of this expression. This is the induced vertical normal stress it is the induced incremental shear stress, and it is the this is expression of vertical magnetic potential induction. Sorry, vertical magnetic induction field. Similarly, in a similar manner, the same status conditions are there. Just we are here, we are just changing the boundary condition 14, 11, 12, and 14. 14 condition we are using. We can get the induced mechanical stress and magnetic potential function for magnetically open case. So the same expression we can get for magnetically open case also. This is induced vertical incremental stress, shear stress, and vertical magnetic induction. So we can see that from through the boundary condition, we can see that at since it is this function is involved, Dirac delta function is involved in the boundary condition. So it shows that at x equal to vt, at this point, that directly below the point of impact, at x equal to vt, this can be impulsive force. The value is very high, suddenly very high, and at other points, that this can be zero here. Right? Okay, so at x equal to vt, so we our objective is to determine the incremental stress at this point, x equal to vt, because if the sudden impact can generate a very high stress and it can damage the structure. So what is the behavior of what is those incremental stresses and magnetic inductions? Okay. And what are the parameters through which we can control this stress? So, figure 2 represents the effect of maximum depth of irregularity, dimensionless irregularity parameter, and parameter for functional gradedness on induced vertical normal stress. So it can be we can see that here curve 1, 2, and 3 represents the variation of maximum depth of irregularity. Here we can see that as the maximum depth of irregularity increases, the induced vertical normal stress increases for both magnetically short and open case. Here 2A represents the case of magnetically short case, and 2B represents the curve for magnetically open case. So for both cases, it increases. And now for it curves 4, 5, and 6 in both conditions, both state magnetic conditions, represents the different cases of surface irregularity. Here, just I have discussed in that part. Here, if x by b equal to 0 represents the rectangular shaped surface irregularity, then x by b lies between 0 and 1. So I have taken the value here 0.5, but any other value can also be taken here, like 0.6, any other value lie between 0 and 1. Here represented the case of parabolic shaped surface irregularity, and when x by equal to 1, that means it represents the case of no irregularity. So here we can see that for the case of rectangular shaped surface irregularity, the induced vertical normal stress is very high. And in the case of parabolic shaped surface irregularity, it is lesser than the former case for both cases. And now when there is no irregularity at upper surface, then the stress is very low. Stress is very low. And again, here curves 7, 8, and 9 represents the effect of the functional gradient parameter here, and it can be seen that as this values increases, functional gradient is increasing inside in the structures, the induced vertical stress, normal stress decreases. A slight decrement we can see here with the increase of functional gradient. So from here we can see that if we can take the irregularity like that, here rectangular shape is very high, parabolic shape it is just low. If we can take just similar kind of irregularity, just we can change the shape here. In this way, then we can reduce the stresses on the upper surface. Okay, and if we just if we can just keep the this functional gradient parameter high, okay, high value for higher value of this, these stresses can be decreased. Similarly, for incremental shear stresses, you can see the same pattern here. Okay, for maximum depth of surface irregularity factor, and the heterogeneity parameter for both magnetically open and short case. This is since now, as I discussed, that it is a linear magnetochemical effect. If we apply any stress here, then magnetic movement can be generated, and these are corrected here. So here we can also see the same pattern here under the effect of all the physical parameters like regulated depth, reactive factor, and the heterogeneity, this parameter of functional readiness. Now here we have discussed, we will discuss that thing here means when the material is non-piezo-magnetic, okay, and for electrically short case and electrically open case. So here I have used this material here, cobalt ferrite. This is a piezo-magnetic magnetic material. Okay. Here we can see that for the magnetically short case, both induce vertical this normal stress and shear stress, both is maximum in the case of magnetically short case, and it is minimum for magnetically open case. Okay, and when the material is piezo-magnetic material, non-piezo-magnetic, then in this case the stress lies between these two cases, magnetically short and open cases. Similarly, we can see the vertical magnetic induction here. So here we can see that for the magnetically short case, it is higher maximum, and for magnetically open case, it is lesser. So these are the through this we can optimize structures that to just reduce the effect of damaging effect of incremental stresses and critical induction. So these are my conclusion also. These are the references that used in these studies. Any questions?
Yeah, if anyone has any questions, please can ask quickly because we are already a little late. If not, we can thank the speaker and we can move on to the next speaker.
Yeah, thank you to the organizers for giving me opportunity to present my work in this book. Thank you. Thank you.
Thank you, Anil. Please, you can stop sharing your screen. Next is Fahim Shahid from Assam. Are you here?
Yes, ma'am.
So Fahim will be speaking on moments of Pusterman sums through super character theory. I don't know whether I pronounced everything properly. Fahim, you please clarify and present your work. And please try to complete it by within 12 minutes.
Sure. And is it visible?
Yeah. Yes, now it is visible and you can make it this full screen. Yes, fine now.
My name is Fahim Syed. I'm a research scholar in the Department of Science and Mathematics from the Indian Institute of Information Technology, Guwahati. My topic for today's presentation is moments of Klosterman sums through supercharacter theory. In this presentation, I'll talk about the introduction to the concept of supercharacter theory, properties and table of supercharacter theory, the motivation behind it, exponential sums, its relation with supercharacter theory and established results, finally the conclusion. So supercharacter theory is nothing but the generalization of something that we already know, called character theory, right? Character theory has already been used in chemistry to study the molecular symmetry of atoms. So supercharacter theory will also be helpful. We'll only discuss about finite groups here. So let G be a finite group and X be a partition of the set Ig of irreducible characters of G, and let Y be a partition of G. Then the ordered pair XY is said to be a supercharacter theory if it satisfies the following three conditions. First condition is if Y contains the identity partition. Second condition, if the number of partitions of G and that on Ig are the same. And the third condition is that if for each X in X, the character sum defined in this manner, sigma X, which is equal to summation of chi of 1 into chi, where chi belongs to X, is constant on each partition Y of Y. If it satisfies these three conditions, then the ordered pair XY is said to be a supercharacter theory. Sigma X in this case is called the supercharacter, where each X belongs to X, and the elements Y belongs to Y are called superclasses, which normally we used to call conjugacy classes. Right? Now, here are a few properties. Like superclasses are union of conjugacy classes. These are not random partitions, they are actually union of conjugacy classes.
supercharacters are also orthogonal with respect to the summation product, just like the irreducible characters we have. The next property is supercharacters span the set of all complex valued functions on G which are constant on the superclasses. Now here we talk about something called supercharacter table. Since we already have something called character table, we expect to have supercharacter table also. And it's constructed the same way as character table. The entries of the table are nothing but the supercharacter values. This is an example of a supercharacter table where Ka is the notation for K1A, the Klosterman sum that we generally know. I'll talk a bit about it in the later slides. Right. Here's a brief idea of the construction of the supercharacter table. I won't go into the details, it's just a first step. A group action leads us to this supercharacter table. What kind of group action? Let gamma be a symmetric subgroup of the general linear group over Zn of order D that is closed under the transpose operation. And let x1, x2 up to xn denote the orbits in Zn power D under the action of gamma. Right? And this group action leads to a supercharacter theory. Of course, there are several steps that I've skipped. There are several lemmas that are required to prove that this group action actually forms a supercharacter theory. Right? The sigma I defined in this manner, the summation of exponent of x dot y over n, where x varies from in xi, and x dot y denotes the formal dot product. Right? These are constants on xi. So the xi's are the superclasses in this case, and the sigma i's are the supercharacters on Zn power D. Right? So next, what we do is we define a matrix using the entries of the supercharacter table. The sigma I xj, these are the entries of the supercharacter table. Using these entries, we form a matrix. This matrix is a bit special, it's useful. It turns out that U is unitary and symmetric. Right? The motivation behind this. What's the motivation? Now, supercharacter theory has an edge over character theory for the following reasons. Now, the first reason is that it is not always possible or convenient to have the irreducible characters or even the conjugacy classes of a group in an explicit manner. Second reason, since supercharacters arise from relatively coarser partitions, the supercharacter table is generally easier to handle. Also, there are often multiple supercharacter theories for a group. For character theory, for a particular group, we only have one particular character table. However, that's not the same in this case. So we might discover interesting results which are otherwise not possible. Next, we talk about exponential sums and how we can relate to supercharacter theory. Let xn be a finite sequence of real numbers, then exponential sums are defined in this form, summation of exponent of 2 pi iota of xn. Right? And there are several exponential sums that have been studied by number theorists. These are the most popular ones, the quadratic cost sum, which is defined in this manner, twice by I, a t square, modulo t. There is the Klosterman sums that I study, and there are the Ramanujan sums defined in this manner. Right? And there are many others. Right? In 2014, J.L. Bromberg et al. Described how a variety of important exponential sums arise as supercharacter values. But just exponential sum arising as supercharacter value is not sufficient. We need proper applications, right? So what happens in 2019, S.R. Garcia and G. Todd used supercharacter tables to connect the sixth moment of Klosterman sums to elliptic curves. As a consequence of this result, the bound for Klosterman sum has also been improved. Now this is the definition for the nth moment of Klosterman sum. Vn is defined as summation ku to the power n, u varies from 1 to p minus 1. So this is the nth moment. And this is the expression for the sixth moment, which is in terms of APEK. This denotes the trace of Frobenius of the family of elliptic curve, PKFP. This is the family of elliptic curve, right? So inspired from this, I have also found the result. And the key lemma to this result is this, that if we follow the same table that we have mentioned earlier, we have seen earlier, and the same notation, then this is the key lemma. So for fixed Zn xk, there is something calledCijk, which denote the number of solutions of this equation, right? And then we form certain matrices like T1, T2, and Tn. Given by this, these are the matrices, which satisfy this special relation Piu equals to UDI, where U has already been defined, and Di is the diagonal matrix, this, right? So if we compare the first entry of both sides of this particular equation, what we get is an interesting result. This is the key relation. From this, Garcia and Todd concluded that Vn is this. So we have a general formula for nth moment, right? So replacing n by any number will get the nth moment. However, it's not that simple to find any number of moment, because this particular term, P1 to the power n minus 2, is not always easy to calculate. In fact, we'll see that for just n equals to 8, the expression gets quite complicated. Next, we consider the following elliptic curves, Ej, given by this, Eij is this. These are families of elliptic curves. These are the notations that I've mentioned. And this is any prime e greater than 5, we have the expression for each moment in this manner. So this AP, EJ, AP, EIJ, these are all sets of opinions of elliptic curves, right? So as you can see, the expression is complicated, and as we go higher, it becomes more and more complicated. Nevertheless, we can at least get some relation between the moments of cluster momentum and elliptic curves. In conclusion, supercharacter theory can be a powerful and elegant tool for number theoretic problems. Although a number of exponential sums have already been studied, there are still plenty to discover. With theory being comparatively a new one, there seems to be ample space to explore further. These are the references. Thank you so much.
Thank you, fine. If anyone has any questions, please, we are very quick. So, if anyone have any questions, please can ask, or you can thank the speaker. And, okay, fine. Thank you.
Thank you,
You
ma'am.
can, yeah, you can close your presentation. You can invite the next speaker, Piyush Boshak from West Bengal. Hi, Piyush,
Yes.
are you here?
I'm here. Shall I put
Yeah.
the
You can just present your slide. Piyush will be speaking on statistical evolutionary analysis and prediction of carbon dioxide emission in Gujarat and Maharashtra, India. Piyush, you can start your presentation, please.
just a second.
Yeah.
Can you see? No problem.
Yes. Yeah, we can see. You can just make it to the full screen. You can just make it full screen.
Yes. Statistical evolutionary analysis and prediction of carbon dioxide emission in Gujarat and Maharashtra, India. Myself is Piyush Boshak, Department of Mathematics, Narula Institute of Technology. So actually there are, in introduction, I can say that there are many states in our India. I have chosen 2 of them to find out what is the emission pattern of carbon dioxide.
Yeah, can you please make your presentation to full screen?
It is full screen.
You can go to the view, I think, or slideshow or view, and then make it full screen, I think.
View.
So make
View. You can go to view and
view, and then view and then normal. No.
So press F5.
F5, yeah.
F5.
Yes.
No improvement, but
Okay, please carry on.
Yeah, you can.
no problem. Actually, the objective of the study is global. We all know that global warming is a serious concern to the scientists due to its alarming situation in the inhabitants, also the existence of life on Earth. One of the major causes of global warming is the uncontrolled emission of greenhouse gases. Out of the greenhouse gases, carbon dioxide is the main culprit, which is available from different sources like fossil fuels, solid fuels, gaseous fuels. The emission fluctuates in space and time from less industrial area to less populated area to higher industrial area and dense population area. And actually this will change. In a dense population area, the emission is much more. In the industry, if it is industrial belt, there will be a lot of pollution, much more. This fluctuation is there. And in this paper, I have just tried out to find out what is the pattern of Gujarat and Maharashtra from using the data set of 1980 to 2000. I would have chosen other state also. There is some other pattern, but for sake of inquiry, I am just finding out this page down. Page down. Oh. Major global source of carbon dioxide are liquid fuels. As you know, from the petroleum, lot of petroleums are burning every day, everywhere, and that is the main source of the liquid fuels. And secondly, solid fuels, which is nothing but coal, is burning every day in thermal industry, thermal power plant, and in every industry there is some requirement of coal. That is the solid fuels. In 2011, carbon dioxide accounted for 84% of US greenhouse gas emission from human activities. In almost all states of India, amount of emission in the last 50 years from the fossil fuel is tremendous. It may be mentioned that India is the fourth largest carbon dioxide emitter in the world. These are information only. Actually, some causes of the global warming, we understand that, but it will be very visual, will be very soothing that the emission part from the motor car, from the power plant and other industrial, there's a lot of carbon dioxide going up. Emission of estimate from inventory of US gases, 2011. There is a segmental part, that is electricity is 38%, and transportation is 31%, industry 14%. This segment will give you how many types of consumption is there, and how many percentage is contribution towards the whole emission of carbon dioxide. Next part is the effect of global warming. That is actually we are achieving towards these positions. We are coming out day by day. We are burning the fuels, and actually will come to the next would come to this fateful situation. Now, we have to understand this problem very clearly, that carbon dioxide is having in the atmosphere, in the Earth's carbon cycle is there. There is an Earth carbon cycle. Carbon dioxide is a component of it. In Earth's carbon cycle, there are all in the way it is just linked up. That is natural circulation of atmosphere, ocean, soil, plants, animals. Everything is linked up in its Earth's natural carbon cycle. But what is happening here? Human activities are altering this carbon cycle, and by adding more carbon dioxide to the atmosphere and influencing the ability of the natural sinks like forest to remove the carbon dioxide. Actually, we know that in the forest there are a lot of plants are there. Plants are that they take out the oxygen and of carbon dioxide and just replace it by oxygen. But day by day we are cutting the forest, and that is why the natural sink is disturbed. So there is a disbalance. That is the much more carbon dioxide is provoking, and whereas the sink of the carbon dioxide is get lost. Carbon dioxide emissions come from a variety of natural sources, that is human-related emission are responsible for that, and that is increasing occurring in the atmosphere since the Industrial Revolution. So far, the Industrial Revolution has started. This is day by day, it is getting difficult and warming up of the atmosphere. I think I can understand this situation. Now, that is, we have to know something about the greenhouse mechanism. In greenhouse mechanism, the solar radiation comes and falls on the surface of the earth, and it has just heated the atmosphere, and the balance is going up to the in space, balance of the radiation. Whereas there is a lot of greenhouse gases, what happens? Sun's radiation come to fall on the earth, and the greenhouse gases, they absorb the heat, they absorb the heat from the solar radiation, and thus less amount of radiation goes back to the space. So this is because of this unlimited, uncontrolled increase of the carbon dioxide, methane, and water, and other nitrous oxide and other gases. These greenhouse gases just facing the problem by warming up the atmosphere in the every day. We're just getting the warming of atmosphere because we have seen that the ice caps are melting. Now, this is a history of the carbon dioxide cycle. That is, this is the nowadays, last 50 years, carbon dioxide emission is shooting up very sharply. And whereas in the earlier one, they are shooting, but not so much. In the earlier stages, that is 1,000 years, 2,000 years back, there are some increment and decrement of the carbon dioxide there. But in the last 50 years, it is warming up very sharply. Some features which I should mention about the emission of carbon dioxide in India. Main sources of carbon dioxide are solid fuels, that is coal. Liquid fuels, that is petrol. Gaseous fuels like LPG gas and cement industry. The amount of carbon dioxide emission for the last 50 years from the fossil fuel is tremendous. India is the fourth largest carbon dioxide emitter in the world. Solid fuel is much more important than the liquid fuels. For the world, solid is to liquid ratio is 33 to 44, where in India it is 68 is to 24. We are just burning up solid fuels, that is coal, too much. This is a dangerous point for us. Ultimately, in the last coming 50 or 75 years, coal will be finished. Emission of carbon dioxide in different states in India for last 30 years is fear-provoking. Now, some anomaly we should understand clearly that population is not the only factor for the emission of carbon dioxide, because we have observed that the Japan and India, Japan has much less population than India. India has having the very record population, but this carbon dioxide emissions in Japan and India have almost same emission pattern, all same emission quantity. It is just observed from the data of Japan and India. Area is definitely not the indicator. India has a vast area, whereas Japan has a small area, but these two countries having the emission pattern of the same category. Economic progress is also not the indicator, because economically, Japan is very much economically developed, but India is not so much developed, as we know. So, but they are having the same amount of carbon dioxide emission. These are studies internally. Some literature review, otherwise this paper would not come in the good way. So previous jobs, the scientists are always trying to find out what is the cause of this greenhouse gas. This Peterson developed an empirical model for the emission of carbon dioxide on economic growth and per capita income in United States. Forge, Yakin, and Sladen has emission pattern has suggested the emission will not decrease unless we get a very big growth in the high level. That means we are day by day developing. If we develop day by day, then requirement of the fuels will be much more, and that is why there is no end of the carbon dioxide emission. Andres et al. Hints that the rate of growth continues to grow until the present times, and the question of enhanced greenhouse warming is coming. So it does not have any limit. Nobody can find any limit for the emission of carbon dioxide. Others are also there. That is, Aflermer and Carson has developed a multiple linear regression model for carbon dioxide emission. Shou, C, and TOCOS utilize ANIMA model to fairly predict the carbon dioxide emission in China and USA. Cram points out that reduction in sulfur emission enhances the warming effect of carbon dioxide from fossil fuel. Chin et al. Constructed a dynamic model utilizing the energy demand applicable in Taiwan. Anyway, there are others also, and after that I start the mechanism of carbon dioxide emission. That is, Gore recommended differential equation for the formulation of carbon dioxide emission. Tokos and Su pointed out that carbon dioxide emission ought to be differentiable function of third degree to the attribute variables. Barnes proposed the differential model of third degree for concentration of carbon dioxide element to the plant. Pasak and Nandi formulated the sum of the states of India as a third degree polynomial for emission of carbon dioxide. So thus we had an idea that a third degree polynomial would be very fruitful in case of carbon dioxide emission in India. So we have started this type of calculation, that formulation of carbon dioxide emission, that is just presented by a polynomial y is equal to a plus bx plus cx square plus dx cube, where x stands for years and abc are constants and y is the emission of carbon dioxide. And this is the polynomial based fit least square method. That is, error is equal to sigma I is equal to 1 to n yi minus a minus bxi minus cx square minus dx cube. And as you know, the partial derivative is done and we get the following normal equations. So far there is no problem. So equation 3 is utilized to obtain the estimate of A, B, C and D, and then estimation of the carbon dioxide emission. Now, just we have supposed that the carbon dioxide emission is calculated, but what about the determination? What is the coefficient of determination that finds out the quality of the estimate? R square is the coefficient of determination is equal to 1 minus sum of square of error by sum of square of total, where R square is defined as the proportion of the total response variation that is explained by the model. So big value, the value it is nearer to 1 will be very accurate model, and value it is less than 1 will be inaccurate model. It provides an overall measure of how well the model fits the data that I have calculated by R square. Yes.
Mr. Vijay, please, can you please, speeding your, you are running out of time actually. So please quickly complete it.
I am trying very best.
Yeah,
so
because other people will also present.
Yes. For the computation of the prediction of the carbon dioxide, we have used the derivative of the equation 1, that is dy dx is equal to b plus 2cx plus 3d x square is computed, and from this derivative we find out the instantaneous rate of change of equation, and by integrating this equation we find out the emission at any point of time. So this is okay. This is just studies are there. Gujarat. In Gujarat state, this is the equation, that is emission of carbon dioxide is equal to minus 2.4 into 10 to the power 9 plus, you can see from the figure, this is the actually carbon dioxide emission. Y is the carbon dioxide emission and X is the time in years. Carbon dioxide emission is just kind of measured in 1,000 metric ton of carbon. The graphical display will be this way. We can see the model data red and the actual status of the data is matching fairly well. And R square calculated is 0.9845, which is fair enough. So in the figure, the change of carbon dioxide emission is compared with the model data And it is evident from the figure that carbon dioxide emission model match well within the actual status of carbon dioxide emission. In recent years, there is some growth leads to the rapid consumption of fuels in automobiles and industry. In recent, there is shooting up. That is because of this. And the coefficient of determination reflect that the fact that we have chosen a very good model. These results attest the good quality of the model. This is the instantaneous rate of change for Gujarat. I have told you that this equation, instantaneous rate of change, will give you this curve, and by integrating the curve, we have got this is the residual analysis. That is the actual estimated data and the observed data. There is actually the mean of the residual is very low, 0.004055. It is very low enough. We want the low enough data. And from this, the prediction of carbon dioxide in Gujarat in 2005, 2009, and 2012 are 21,123, 22,495, and 23,578 thousand metric ton of carbon, respectively. Now we are doing the same process for Maharashtra only. This is the emission curve in Maharashtra. This is the actual figure of the model data and the observed data. The green one is observed and the red one is model data. It is evident from the figure that the carbon dioxide emission matches well with the actual data. So an R square is found to be 0.9917. It's fairly good, very much good, I can say. It is not 1, only 0.9917. The result attests that the good quality of proposed model for the emission of carbon dioxide in Maharashtra. This is the instantaneous rate of change for Maharashtra, and from there we can find out the prediction of the carbon dioxide emission in 2005, 2009, 2012 as 33,138, 23,816, and 11,414 thousand metric ton of carbon. This is the residual analysis for Maharashtra, and we want a carbon-free world. There is the indication. So we have to live. No, if we die, what shall I do? So we want a carbon-free world. And this is some conclusion. Pattern of CO2 growth is not uniform. As you know, I have discussed this. The pattern changes from less industrial and less populated to densely populated part of the country. We have developed the polynomial emission of carbon dioxide from Gujarat and Maharashtra, considering the different suitable variables, namely fossil fuel, cement, and gas flaring. Then only 2 points are left. That is, in recent years, the rapid growths are observed leading to the rapid consumption of fuel in automobiles and industry in Gujarat, where emission is somewhat controlled in Maharashtra. In Maharashtra, it is somewhat controlled, but in Gujarat, still emission is increasing. The study may be the theoretical basis, for the future research of carbon dioxide emission in different states and countries, and our model may be utilized for function and strategic planning and application for declining the terrible global warming in near future. These are the references, few references are there. Thank you.
Thank you. If anyone have any question, please you can ask. Okay, if not, then we can move on to the next speaker, and we can thank the speaker. Mr. P, you can stop sharing your screen and we can move. So the next speaker is Sushant Mondol. Sushant, are you there? Hello? Sushant, are you there?
Yes, I am sharing my screen.
Yeah, you can share your screen and start presenting. So Sushant will be speaking on convective heat transfer and entropy analysis on MHD, Maxwell nanofluid flow involving gyrotactic microorganisms.
Is my screen visible?
Yeah, your screen is visible. You can make it to full screen and start presenting. So please complete it by 12 minutes, everyone, please.
Okay. Good evening to all of you. Am I audible? Hello?
Yeah, you are audible.
Yeah, you are audible. Okay. First, I would like to introduce myself shortly. Myself, Sushant Mandal. I am associated with the Department of Mathematics, St. Paul's Cathedral Mission College, Kolkata. I would like to convey my thanks to the organizers of this conference for giving me a chance to present my work on this online platform. Today, I am going to talk on convective heat transfer and entropy analysis on MEHD Maxwell nanofluid flow involving gyrotactic microorganisms. I have worked out this problem under the guidance of Dr. Gopal Chandra Seeth, Department of Mathematics, Jadavpur University, Kolkata. This is the outline of my presentation. First, I would like to give a short introduction. Then I will mention some literature review. Then I will spend few minutes to discuss the mathematical formulation of the present problem. After that, I will introduce the numerical method that I have used to solve the mathematical problem. Then I will mention some final conclusion. Finally, I will show some of the references. Now I am going to introduce nanofluid and entropy generation. Nanofluid is a fluid that is created by distributing solid nanometer size particle with dimension less than 100 nanometer in the base fluid. Nanoparticles are made of metals, oxides or carbides such as aluminum, copper, aluminum oxide, copper oxide, silicon carbide, etc. Classical heat transfer fluid such as ethylene glycol, water and engine oil have limited heat transfer capabilities and cannot fulfill modern cooling requirements. On the other hand, thermal conductivity of the metal is extremely higher in comparison with the conventional fluid such as oil, water, ethylene glycol. Suspending the ultrafine solid particle into conventional fluid such as oil, water causes an increase in the thermal conductivity. Nanofluids has many unique characteristics in the field of thermal engineering. Nanofluids are used in different engineering applications such as metal extrusion, polymer processing, oil exploration, etc. The convective heat transfer in the porous medium saturated by nanofluids has many important in heat transfer such as heat transfer in nuclear reactor, fuel cell, solar system, electronic cooling devices, etc. Entropy generation is a method to quantify the thermodynamic irreversibility in a fluid flow process. The first law of thermodynamics is simply an expression of conservation of energy principle, whereas the second law of thermodynamics states that all real processes are irreversible. Entropy generation measures the level of irreversibility associated of the real process. As entropy generation takes place, the quality of energy decreases. In order to preserve the quality of energy in the fluid flow process, we need to reduce the entropy generation. To measure the entropy generation, we need to study the distribution of entropy generation within the fluid volume. Thus, we need to determine the factors responsible for the entropy generation. In this present analysis, we have quantified entropy generation in terms of a beautiful number called Bejan number. Our main objective is to find the flow parameters which can minimize or at least reduce the entropy generation of the fluid flow problem. With this aim, we have formulated our problem. This slide shows some of the relevant literature reviews. In order to formulate the physical problem mathematically, we have consider flow configuration in cylindrical polar coordinates of MSD steady two-dimensional flow of an incompressible homogeneous viscous and electrically conducting Maxwell nanofluid passed over an inclined stretching cylinder with gyrotactic microorganisms. Here, the axial direction is taken as the z-axis and the radial direction is taken as the r-axis. The fluid is flowing along the axial direction. The flow of viscous nanofluid embedded in a porous medium take place in the region r greater than equal to a, where a is the radius of the cylinder. An external magnetic force of magnitude B0 is applied in the radial direction, that is the perpendicular to the flow direction, flow of the motion. Influence of thermal radiation, heat generation, and viscous dissipations are taken into account in the energy equation. Thermophoresis and boundary motion effects on nanoparticles are treated as per Bongiorno's model. We have excluded the induced magnetic field from our consideration by considering the low magnetic Reynolds number. Further, we have assumed that the nanoparticles will not disturb the swimming velocity of the microorganism. The cylinder is considered to be stretchable. The temperature of the base fluid is considered less than 42 degrees to meet the living condition of the microorganisms. And we consider radiative heat plus as per Rosenthal approximation. This is the schematic diagram of the physical problem. Under the above mentioned assumptions and above choice of coordinate system, the flow equations in boundary layer are given by 2 to 6. Equation 2. Equation 2 is the quantity equation. It represents the conservation of mass. Equation 3 is the momentum balance equation. Equation 4 is the equation of energy. That is, it represents the conservation of energy in terms of flow variables. Equation 5 is the nanoparticle concentration equation. It represents the conservation of concentration of nanoparticle, and 6 represents the conservation of gyrotactic microorganisms. The appropriate boundary condition for the present analysis are given by 7 and 8. 7 represents the boundary condition at the stretching cylinder, and 8 represents the boundary condition far away from the stretching cylinder. First boundary condition is the no slip boundary condition. Second boundary condition shows that there is no suction injection, and next two boundary condition is the convective heat and mass transfer. Where AC represents the heat transfer coefficient of the stretching wall, where MC is the mass transfer coefficient of the stretching wall. We have considered radiative heat plus according to the Rosenthal approximation keyword, and now using Taylor series approximation of T to the power 4 about T infinity, we have del R QR by 10. Using 10, the energy equation is modified by 11. Now we define the following similar variables to transform the given set of partial differential equation into a set of ordinary differential equation. Here eta is the dimensionless space variable, psi is the dimensional stream function, f is the dimensionless stream function, theta is the dimensionless temperature variable, phi is the dimensionless concentration variable, I is the dimensionless nanoparticle, chi is the dimensionless density of microorganism. Where A is the radius of the cylinder, L represents the difference length. Now we compute the velocity component from stream function. We get the expression of U and V given by 13. Since we are computing the velocity component from the stream function, the quantity equation is automatically satisfied. And the non-dimensional form of the equations are given by 14 to 17. These are the governing equations in terms of non-dimensional variables. And the non-dimensional form of boundary conditions are given by 20 and 21. In the above formulations, the arising non-dimensional parameters are listed here. For example, MA is the magnetic parameter, gamma is the curvature parameter, PR is the Prandtl number, R is the thermal radiation, etc. These are the controlling parameters of the present analysis. These are listed here. As I mentioned at the very beginning, entropy generation measures the thermodynamic irreversibility present in the fluid flow process. In the present analysis, the total entropy generation per unit volume is given by 22. 22 shows the different source term of the entropy generation. First two term represents the entropy generation due to heat transfer, and this term represents the entropy generation due to fluid friction, entropy generation due to nanoparticles interaction with base fluid, entropy generation due to presence of magnetic field, and entropy generation due to interaction with microorganism, and last one is the entropy generation due to porosity of the medium. And now, non-dimensional entropy generation number can be calculated using 23. Now I am going to introduce Bézier number. Bézier number is a beautiful number to display the dominance between the distribution of entropy generation owing to the heat transfer and the entropy generation due to other sources. The Bézier number, which is the ratio of entropy generation due to heat transfer over total entropy generation, is given by NH by NG. NH is the entropy generation number due to heat transfer, including thermal radiation. NG is the entropy generation number, total entropy generation number. We have used shooting method along with Rangi-Kuttar-Felbert's integration technique to solve the mathematical model. The shooting method uses the method used in solving initial values problem. We have used Rangi-Kuttar-Felbert's integration technique as initial value solver method. This is done by assuming initial values that would have been given if the ordinary differential equation were an initial value problem. The system of equation together with the initial condition are numerically solved by employing fourth order Rangi-Kuttar-Felbert's integration method along with the shooting technique. Shooting technique is used to capture the missing initial condition using supplied boundary condition at the other end. With an aim to solve above mentioned equation by Rangi-Kuttar-Felbert's integration method, it is necessary to reduce the higher order equation into a set of first order ordinary differential equations. The system of first order equations are given by 25 and the initial condition are taken as 26. The shooting method continues until the condition given in 27 is satisfied. Now I am going to present my finding graphically. Figure 1 shows that how the behavior of the velocity profile gets affected for the variation of porous permeability parameter Pm and curvature parameter gamma. Fluid velocity slows down for augmented values of porous permeability parameter Pm. For higher values of Pm, the medium offers more resistance. As a result, fluid velocity diminishes. But the opposite trend is occurred for the variation of curvature parameter gamma. The velocity rises at the vicinity of the stretching cylinder as the curvature parameter gamma increases. Actually, the contact area decreases upon an increment of the curvature parameter, so resistance of the fluid decreases or reduces and the velocity rises. Figure 2 shows that the alteration of velocity for the non-Newtonian behavior of the fluid through Deborah number, b time. The velocity gets lower for higher values of b time. A relaxation time enlarges due to higher value of b time. That is why velocity gets lower. These are the more important result of the Bézier analysis. These are the temperature variations for different values of the magnetic parameter and Brinkman number. These are also the variation of concentration profile and variation of motile density profiles. These are the Bézier profiles. And interesting, this result is very interesting. An interesting behavior of the Bézier profile for various curvature parameter gamma is depicted in this figure. Figure explains that Bézier number is minimum at the stretching wall and it increases up to certain distance from the stretching wall. After the behavior of the Bézier profile depends on the magnitude of the curvature parameter. Next figure, the last figure, shows the Bézier profile in the presence of bioconvection of microorganisms. Based on these, the final conclusions are these. These are the final conclusions. And these are the some of the references. Thank you.
Okay. So anyone having any question? If not, then we thank the speaker, Sushanto, and you can stop sharing your screen. So we move on to the next speaker, Ashik Hussain Mirza. Are you there?
Yes, ma'am. Am I audible?
Yes, you are audible. So you can start sharing your presentation. Our next speaker will speak on ascendancy of thermophoresis with the chemical reaction on MHD fluid flow along an inclined surface in presence of heat and mass deportation. Ashik, you can start your presentation.
Ma'am, is it visible?
Yeah, if it is visible, you can make it to full screen.
Okay.
Okay, yeah.
Okay. So thank you so much giving me this opportunity to introduce my paper in the 15th International Limbic Virtual Conference on Mathematical Sciences for Advancement of Science and Technology. So my name is Ashik Hussain Mirza. I am doing my PhD under the supervision of Professor Rita Chaudhary, ma'am, in Guwahati University. The title of this paper is Ascendancy of Thermophoresis with Chemical Reaction on MSD Fluid Flow Along an Inclined Surface in Presence of Heat and Mass Deportation. So abstract of this paper is the ramification of two-dimensional viscous MSD incompressible fluid cavorted by an inclined surface in perseverance of chemical reaction, thermophoresis and heat source have been explored. The concurrent upshot of constant heat and mass flux is in consideration of uniform magnetic field is also taken into account. Here I consider the suction velocity at the surface is constant. So here the problem is solved by numerical technique. The pertinent property of overall structure of the fluid motion are elucidated with graphical illustration. So there are lots of application in this type of fluid. So some of the application are intersected in the field of industrial and chemical processes. So these are some keywords that I have used in this paper. So first one is thermophoresis. So this is the phenomenon observed in the mixture of mobile particles where the different particles type exhibit different responses to the force of a temperature gradient. So second one is MHD. This is the full form of magnetohydrodynamics. So this is the in magnetohydrodynamics is the study of the magnetic properties and behavior of electrically conducting fluid. So next one is shearing stress. This is the viscous drag per unit area. So Nusselt number. So this is the rate of heat transfer. Generally, we consider the ratio of convective to conductive heat transfer across a boundary. And the last one is Serud number. Now this is the ratio of convective mass transfer to the rate of diffusive mass transport. So mathematical formulation of this problem. So here I consider the two-dimensional steady viscous MSD fluid stream across a porous surface cavorted by an inclined surface in account of chemical reaction and thermophoresis. So here the fluid is transmitted along x bar direction and y bar axis is taken normal to it. The effect of magnetic Reynolds number considered to be very small. So here all the forces acting on the fluid are assumed to be constant except the body forces. So since the plate is infinite length, so therefore all the variables are function of y only. So this is a governing equation. So first equation shows that the equation of continuity. So from equation of continuity, first equation is equation of continuity. So next one is equation of momentum. And the fourth equation is equation of energy, and the last equation is equation number 5 is equation of concentration. So equation 6 shows the boundary condition for this. So these are some non-dimensional parameter. So equation 7 shows that the non-dimensional parameters of this problem. So here f eta is the velocity, eta is the distance, pr is the Prandtl number, sc is the Schmidt number, theta is the dimensionless temperature, c is the dimensionless concentration, alpha is the permeability parameter, gr is the thermal Grashof number, gm is the solutal Grashof number, m is the magnetic field parameter, e is the Eckert number, kr is the chemical reaction parameter, and q is the heat source parameter. So here Vt is the thermophoretic velocity. Equation 8 shows that the thermophoretic velocity, where Kds is the thermophoretic coefficient, and the value of Kds is from 0.2 to 1.2. So here Cs, Ct, C1, C2, etc. are constant. Here tau is the thermophoretic parameter. So after putting the non-dimensional quantities in the governing equation are transformed into this non-dimensional equation. So equation 11 to 13 are the non-dimensional equation. So this equation 14 is the modified boundary condition. So here we used the numerical technique, that is to solve this problem using the MATLAB Boolean solver BVP 4C along with the boundary condition 14. So results and discussion. So in figure 1, the sequel of magnetic field parameter lessen the fluid velocity all over the boundary layer region because the existence of magnetic field in an electrically conductive fluid commences a force exclaimed Lorentz force, which perform against the flow if the magnetic field is solicited in normal direction as the current problem. So this category of resistance force slows down the fluid velocity. So figure 2 represent the effect of velocity with solutal Grashof number. So here we see that an increasing order of velocity profile are observed for increasing the values of gm. So figure 3 excels the rising nature of velocity profile for variation of permeability parameter alpha. So here, whenever we increases the inclination, that is phi, the velocity decline. So figure 5 shows that the diminishing trend of velocity in perceived form development of Kr. So figure 6 discloses the velocity sketch for Grashof number. So it is noticed that the velocity elevates for advancement of Grashof number, that is thermal Grashof number. So in figure 7, with the variation of Q, that is the heat source parameter, the temperature is accelerated. Figure 8 shows increasing trend of temperature profile with the hike of E, that is Eckert number. So temperature profile decline with the advancement of Prandtl number. So this is shown by the figure 9. So in figure 10, a reduction trend of concentration profile is described for tau, that is thermophoretic parameter. So in figure 11, a rising nature of concentration profile is detected in case of magnification of Kr, that is chemical reaction parameter. So figure 12 reveals the decreasing trend of concentration profile with the rising of Schmidt number. So figure 13 delineates upshot of Grashof number on shearing stress against M. The shearing stress enhances with the hike of magnetic field parameter. So figure 14 shows the upshots of Grashof number on shearing stress against alpha. So the shearing stress excels with the enhancement of alpha. So figure 15 declares advancement of Grashof number on shearing stress against Kr, that is chemical reaction parameter. The shearing stress increases with the increment of chemical reaction parameter. So with the growth of Grashof number, the rising trend of Nusselt number versus Eckert number is perceived. Figure 17 excels the essence of Sherwood number against tau, that is thermophoretic parameter, with the magnification of Grashof number. So the conclusion of this paper is the fluid motion is impeded due to the implementation of magnetic field, inclination of plate, chemical reaction, but expedites under the exertion of thermal Grashof number, solutal Grashof number, and permeability effect. The fluid temperature is retarded under the influence of Prandtl number, but rises due to the application of heat generation coefficient and Eckert number. The variation of Schmidt number and thermophoretic parameter diminish the concentration of the fluid, but opposite trend is perceived in case of chemical reaction parameter. The magnitude of the drag force on the plate against magnetic parameter, inclination of the plate, and permeability parameter excels expansion under the impact of thermal Grashof number. The effect of thermal Grashof number causes the rate of heat transfer from the plate to the fluid to expand. And the last one is the mass flux surges under the sequel of thermophoretic parameter. So these are some references that I have used in this paper. So thank you so much.
Okay, so thank you, Ashik. Anyone having any question?
Can I stop my presentation, ma'am?
Yeah. I think no one is having any question. So we can move on to the next speaker, and we thank Ashik.
Thank you, ma'am.
Okay, so Tapas, are you there? Our next speaker is Tapas Haldar from.
Yes, ma'am.
Okay.
Ma'am, I am audible?
Yeah, you are audible. You can share your screen also.
Okay, ma'am.
Tapas will be speaking on analysis of the Love type wave dispersion in non-local elastic heterogeneous medium over a orthotropic half space. Okay. Tapas, you can carry on your presentation. And please try to finish it by 12 minutes. I mean, by 6.
Madam, my screen visible?
Yeah, your screen is visible.
Okay, madam. I am Tapas Haldar, Assistant Professor, PRMS Mahavidyalaya under Bankura University, Bengal. Today, my presentation, my paper, analysis of love type wave dispersion in a non-local elastic heterogeneous medium over a orthotropic half space. What is the wave? The idea is the wave caused by the tossing a stone in a pond. What is a wave? Wave is the disturbance that the transfer energy. Wave are common in nature. Light is a wave, sound is a wave. Wave are periodic in both space and time. Different type of the wave, 2 type of the wave, mechanical wave and electromagnetic waves. Seismic wave is the earthquake and travel through the body of earth and over surface of earth. Seismic wave type, 2 type of seismic wave, surface wave, one surface type of surface wave, love waves and L waves, and second body wave, P waves and S waves. Love wave, one kind of surface wave, they vibrate the ground from side to side with no vertical movement. Mathematical computation of the love wave propagation. Geometry of the problem. My paper, there are two medium. First medium, non-local elastic non-homogeneous medium with thickness D, and second layer non-local elastic orthotropic semi-infinite medium with initial stage P. Solution of the non-local non-homogeneous medium, the equation of motion of first layer with thickness D, the displacement component U1, V1, W1 along X, Y, Z axis direction, then without body force, the equation of motion of this equation 1, where tau ij are the elastic increment component of stage and rho is the density of upper solid medium, that is first layer. Now Hooke's law, the state strain relation of the equation 2, let us consider mu equal to mu 0 a to the power az and rho equal to rho 0 a to the power az, where mu 0, rho 0 are the values of the ratio of the shear moduli at z equal to 0 and a is the constant. Now the lap type wave condition along x direction u equal to 0, v1 equal to v2 xyz function and w equal to w1 equal to 0. Now, corresponding stress-strain relation due to lap-type wave propagation in the non-local elastic heterogeneous or non-homogeneous medium gives the equation 6. Using stress-strain relation 6 and lap wave condition 5 and non-homogeneity relation 4 in equation 1, we have and calculating the equation 7. Let us consider the harmonic solution V1 equal to Vz e to the power I xk minus omega t, where omega equal to ck is the angular velocity, c and k are the phase velocity and wave number respectively. Then the equation 7. Now obtain the equation 9. Now solution of the equation 7 give V1 equal to a cos mz plus a2 sin mz and e to the power this, where m square equal to this part and a1 a2 are the arbitrary constant. This is the dispersion solution of the upper non-local non-homogeneous elastic medium. Second layer, the lower non-local elastic orthotopic semi-infinite medium is considered under the initial stage P, which act along x direction. Then the equation of motion in non-local elastic orthotopic median absent of the body force. Then the equation obtain the equation 11 with the help of lap wave condition 5 and stress-strain relation. Then the equation 12, where U2, V2, W2 are the displacement component in the medium along x, y, z direction, where P is the initial stage, Q1, Q3 are the shear moduli and ρ1 in the density in the second layer. Now using the same methodology of the upper layer, the solution of the equation 11, the lower non-local orthotopic medium can be taken of the form equation 13. Now the solution 13 satisfies the condition. Now the equation 11 satisfies the condition limit z tends to infinity, v2 tends to 0. Therefore, the equation 13 may be taken, v2 only negative part. This is the displacement equation of the lap type second layer, or that is orthotopic layer. Boundary condition. At the upper boundary condition z equal to minus d, the stress component equal to 0. At z equal to 0, then stress component first layer and second layer are same. And z equal to 0, then first layer, second layer are continuity of the displacement component, that is V1 and V2 are same. Now we are ready to write the dispersion relation with the help of boundary condition 15 to 17 on the equation 10 and 4, and we get the equation 18, where beta 0, beta 1 are the shear wave velocity of the layer and semi-infinite medium respectively. Then the equation 18 are record lap type dispersive wave in non-local elastic non-homogeneous medium over a non-local elastic orthotopic semi-infinite medium. Some particular cases, case 1, when the lower semi-infinite medium is isotopic, then Q1, Q3 equal to mu1, then the above equation 18 we take the equation 90. The equation represent the dispersive wave in non-local non-homogeneous medium over a isotopic homogeneous half space. Case 2, if the upper layer is considered the homogeneous, that is A by K equal to 0, but lower semi-infinite medium is orthotopic, then the equation put the A by K equal to 0 and equation 18, and then we have equation 20. These equations are dispersive in non-local elastic homogeneous medium. Case 3, in case the lower orthotopic medium is free from initial stage P equal to 0, then the equation 21. Same particular case 22 and same particular case 25. numerical result, numerical dispersion relative of the describe the using MATLAB software to study the effect of difference parameter. First, we choose difference paper, Manna et al. And Ortho and Kondo et al. Rigidity this choose and density this parameter vary the different range. Then difference figure, different graph, limitation of the dispersive curve with respect to the wave number, the life type wave in non-dimensional difference range. Some importance graphical presentation. Finally, conclusion this. Our paper, some important reference. Thank you. Thank you, ma'am.
Okay, thank you, Tapas. So if anyone having any question, please you can have you can ask some Tapas, and or we can move on to the next speaker if no one is having any question. Okay, so
Thank you,
thank
madam.
the speaker. Yeah, thank you, Tapas. So the next speaker is Sarbojit Kaur from Punjab. Are you there, Sarbojit? Sarbojit, are you there?
Hello.
Yeah, Sarbojit.
Good evening. My voice is audible for you?
Yes, yes, it is audible. And so Sarvajit will be speaking on technology of acceptance model for adoption of e-learning tools during COVID-19.
Should I start?
Sarvajit, yeah, you please share your screen and you can start your presentation.
Okay. My screen is visible to all of you?
Not yet, not yet.
Can you see an arrow box at the bottom of your screen? Yeah.
Now it is visible to you, sir?
Not yet.
Not yet.
Can you see an arrow button, an arrow within a box?
Yes, I have put the arrow button, sir.
Yes, then you have clicked on your entire screen.
Yes.
Then can you see a big box where your screen is visible and at the bottom you can have share and cancel?
Now
yes.
It is visible?
Yes, yes.
Yes, yes, now it is visible.
Okay. Is it visible to all of you? My screen is visible?
Yes.
Yes, your screen is visible.
Okay, good evening, everyone. Myself, Sarabjit Kaur, research scholar at CTU from Punjab. In the Department of Mathematics, I'm presenting the research based upon technology of acceptance models of the adoption of e-learning during COVID-19. So what is the technology of acceptance model? This paper is based upon the different technological models that will be useful for the e-learning tools, and with the help of e-learning tools, how the student responds in the education era. This research is based upon the questionnaire that will be help for the student to adopting the new technological tools, new e-learning tools, which compare to face-to-face and traditional teaching methodologies in rural area of Punjab. Last 2 years, we see that during the COVID crisis, our education system is based upon e-learning. So many technologies are developed regarding COVID-19, which is very helpful for their students as compared to their traditional learning face to face. As the earlier students, adoption of e-learning, maximum them students focused on the theoretical models. That theoretical model, for example, TAM stand for Technological Acceptance Models, which very helpful for the adoption of e-learning. So the main purpose of the discoveries is behavior intention, TAM adoption model, which are suggest for the how to use your technology for the education area and how it can be helpful for their students, especially for the Punjab in rural area. So this is a literature view. Last some authors, some researchers, what they have opinion about regarding e-learning, adoption of e-learning technological models. In 2003, they are considered that learning participation in online is very helpful for their students. Wang et al. 2003, they discovered that education community regarding adoption of higher education, they have 5 stages, which has not produced to accessible for the using e-learning, but also contain their face-to-face distributions. Najinga 2011, they discovered that technological offering approach regarding teaching learning process that will be helpful for the adoption of the subjects. Chow Ho 2001 compared 3 models, TAM, that is Technological Acceptance Model, TPB, that is Theory of Planned Behavior. They 2 models are help for the professional settings. The consequences specified that TAM, that is Technological Acceptance Model, bigger than the Theory of Planned Behaviors. Dishaw, Strong and Bandy 2004 suggested that the models are required individual characteristics, task, models to improve the UTAT, Unit Defined Technological Acceptance. So these are the adoptions of models for the e-learning. There are some models, that is theory of reasoned action, social cognitive theory, diffusion of innovations theory, motivational models, use of gratifications theory, the model of PC utilizations, theory of interpersonal behavior, theory of planned behavior, theory of acceptance, and preserved features of the innovations theory. So first of all, we have a theory of reasoned action. This theory have 4 main aspects, that is attitude towards the behavior, subjective norm, and subjective intentions. Intention, sorry. Every theory has some strong point and some weak point. That is why, due to giving a efficient weaknesses to improving the weaknesses, we are consider the another theory planned. So what is the main positivity of the TR, that is theory research? TR is unique as a maximum essential significant principle for human behavior. The main purpose of this theory is influence attitude and intention. The behavior can be a positive or negative both. This TRA also based upon the perceptions of the human behavior. But here is some weak point of TRA, that they assume that totally under volitional control. They have weak point that the performance might be observed in the address of weaknesses theory. So this is a next theory of planned behavior. Theory of planned behavior giving us stress on intention and behavior both. Behavior believes attitude, nominative believes subjectives, and control believes preserved behavior control. So what is the main strength of a theory of planned behavior? That it is based upon the practical behavior theory, and this theory is lengthy as compared to TRA. This theory is based upon the hypothesis to be interactive control. But here is some negative point of theory of planned behavior. First of all, it does not give any supplementary variables, motivational, past experience, purposes, etc. It adopts the personal opportunity. Although it does not reflect the nominative influences, it does not giving a reflect on economical factors. It based upon only influence personal intention. Next, we have technological acceptance model. So we have four factors: preserved usefulness. Preserved usefulness means how to use, preserve, easy to use, how we can adapt slowly continuing, slowly adapted a technological, and it depend upon the behavior intention to use and what is the actual system of use. So what is the main strength of a technological acceptance model? Technological acceptance model is the supremium than the another theory. Mostly in 2007, they discovered Microsoft Office, PowerPoint, and new technological emails. These are very helpful for e-learning. But in technological acceptance model, also giving a significant model for the teaching purpose by using the new technology. Weaknesses of TM. The main weakness of TM is it is a self-determined behaviors. All another, it concentration on the statistic system. It have been organized, controlled to environment and mandatory for all these situations. Diffusion. Diffusion innovative theory is very important theory. In this theory, we are going for slowly adoption of the technology. It is based upon early adapter, early majority, late majority, and laggards. Laggards stand for that a person who learn, who experience, continuing slowly. So next we have some strength of diffusion innovative theory. It gives the improvement for the hypothetical views. Normally in case of mathematics, everything is based upon the assumption and hypothesis. During COVID-19, seen that there are some difficulties for the student as well as the teacher, especially in case of rural area, how to learn their new technology. So these are some models like diffusion and TAM and TIB, which helpful for the person, helpful for the students, and helpful for the every influence single person to adopted the new technology, new networks in the case of e-learning tools. The main strength of the diffusion innovation theory to peer discussions. Before giving the teaching learning process, it is a peer discussion based upon that. Diffusion researcher believes that there are 5 different segments: early adapter, early majority, late majority, and laggards. The main weakness is that this model does not participate corresponding to different situations. It is not applicable in some different situations. Every essential case, there are significant non-adoption, non-described, and how to relate it is supplementary reason. In case of institution, in the institution, innovation research is beneficial for progressive system, for the adoption plan, but sociologistic, it can't be applicable. First version, TAM, that is external variable, preserved usefulness, preserved easy to use, behavior intention, and usage behavior. In 1986, the main strength of TAM revised first version, accept their informations, accept their known technologies, accept the how to use the new technology, and acceptance model by Davis 1996. They giving a practically procedure for the technological hypothesis. The main weakness of first version is that it not proposed in case of business, universities, and essential hypothesis in discrete observation. This model can't be received the information in ICT. TM is not appropriate and not essential in case of companies, firms, and libraries. So this is a second revised TAM. After seeing the weaknesses of the TAM1, the new model was discovered. This model is based upon experience, volunteers, jobs, outputs, and images and their subjective norms. So main strength of TAM2 is based upon the purpose that preceding the application, use the preceding application, apply in their early use, and it provide the purpose of the constant use, how to use your new technology and new influence, what is the influence of the new technology on the individuals. TM only concern the performance of the operators. they not assess the subjective norms. This is the main weakness of the TAM2. The next TAM3. For removing the weaknesses of TAM2, the scholars, the researchers have discovered TAM3. It is based upon new parameters are added like computer self-efficiency, perceptions of external control, computer playfulness, result. So in case of these TM3, we have some strength. TM3 using 4 different categories. First is individual difference. Every person have different point of view regarding the information technology. System features, system characteristics. Every technological systems have different features. Social influence, what is the influence of the society regarding that situations, and which facilities are provided for the factors of the usefulness. In TM3 third research models, computer concerns are very important. It is helpful to for the all the individuals or the faculty members and all the students in the education era for the computer efficiency. TM3 research model is also established in case of real world IT application. In this model, we can use the application of IT sectors. In weakness of TM3, this is the only conceptual, it is not conceptual appropriate for this study. It suggested some investigations for the removing the criticisms. So what is a comparison between the discussions of above the theory? In Sun 2003 and Susanna 1994 initiate that hypothetical and self-reports practice 61 progress business students but not hypothesis revised TM. This is the main comparison. In 1994, TM was not hypothetically revised. In study of individual calculating accepting firm, Craig Kavya found that usefulness of the strong direct effect of the technology in case of adoption of e-learning. Sun 2003 exposed that ultimate stimulus affecting of the construct to acceptance of the technology. And Vanilla 2004 exposed that initiating the connection between the perceived and attitude of the individuals regarding the adoption of the technological models. So my next research plans to adoption of IT smart home services, which helpful for the examination point of view, also value-based adoption models in case of adoption of e-learning, like regarding these crises like COVID. In sometimes everything is not education system has suffered. So this is my next research plan. Thank you, everyone.
Hello? Yeah.
Hello.
If someone has a question, please you can ask or you can thank the speaker. And I think one more speaker who was not present is on the line. So I think he has already arrived and ready to present. So we can ask Omorto. If you are ready, you can
Yes,
you
ma'am.
can share your screen. And please,
Yes.
Sharbajit, you can please stop sharing your screen. And
Okay.
we can move on to Amartya. And Amartya will be speaking on sorry, the assessment of generalized process capability index CPY under generalized Lindley distribution. Amartya, you please share your screen and start your presentation.
Okay. Am I audible? Hello? Hello, am I audible?
Yes, audible.
Okay. So, good evening all. To start with, I must sincerely thank my research supervisors, Dr. Sudhanshu Shekhar Maiti from Vishwabharati University and Dr. Arindam Gupta from Vardhaman University, and the paper collaborator, Dr. Mriganko Mouli Choudhury, in this regard. I also thank the organizer for giving me this opportunity to deliver my topic here. My topic of presentation is Assessment of Generalized Process Capability Index, CPY, under Generalized Lindley Distribution. Myself, Amartya Bhattacharya, I'm a statistical officer on NATMO, Government of India, Calcutta. Process Capability Index shows the relationship between the process rate and the consumer specification in terms of a numeric value. Process Capability Indices aims to quantify the capability of a process to meet some specification that are related to a measurable characteristics of its product items. Process capability analysis is an effective means to measure the performance and the potential capability of a process. Process Capability Index are abbreviated as PCIs. The PCIs are widely used in industry for evaluating a manufacturing process, whether or not it can be produced article within the specified items. This specification has two limits. One is lower limit and is upper limit, which is abbreviated as capital L and capital U, and we have a target value. The first approach, many process capability indices, was developed starting from the CP, which is U minus L divided by 6 sigma, given by Zuran in 1974, where L and U are the lower and upper specification limit assigned by the consumers, and 6 sigma is the process spread of quality characteristics X manufactured by the producer in the industry. Some other notable matrices are CPK by Kane, CPM by Taguchi, and CPMK by Choin-1 and Pan at 1992. All these indices are developed under the assumption of normal distribution, but in practice, non-normal setup is introduced in many situations. Hence, the generalization of these process capability indices is necessary. Now we come to the point of the generalized process capability index. Generalization of process capability indices for non-normal distribution attempted by Clements et al. All the measures deal with the characteristic represented only through the continuous distribution. One faces the problem with the process of having a characteristics those whose values are discrete. Another approach is to use the ratio of two proportion. Some authors have dealt with this. The ETCs suggested are meaningful regardless of whether the studies process is discrete or normal. The generalized process capability index, which is abbreviated as GPCI due to Mighty et al., is abbreviated as CPY. When the process evaluates the lifetime of a product, a longer lifetime implies a better product quality, higher reliability, and that the process is capable. In such a situation, the lifetime of product may follow the larger the better quality characteristic. Now we come to the point of a Lindley distribution. The Lindley distribution is basically a continuous distribution which plays a vital role in modeling and analyzing the lifetime of a manufacturing products in the industry. For more flexibility in many mathematical properties like mode, moment, skewness, kurtosis, and etc., quality analyzers are more interested in using in a continuous probability distribution, namely the Lindley distribution due to Lindley 1958. The probability density function and the cumulative distribution function of the Lindley distribution is given by this and this. Now we come to the point of the generalization of Lindley distribution and its natural discrete version. The distribution have a generalized by a list of authors. We call the proposed distribution of Buchahead as the one-parameter polynomial exponential family of distribution, and the PDF of the one-parameter polynomial exponential distribution is given by this expression. The distribution can also be written as this expression, and the corresponding CDF is given by this. The advantage of the index CPY is that it can be assessed even if the exam process has a character whose value is isolated, that is discrete.
A natural discrete analog of the one-parameter polynomial exponential distribution has been generated using the fact that the geometric mean and the negative binomial distribution are the natural discrete analogs of the exponential and the gamma distribution respectively. The motive have been reflected in Mighty et al. In 2020 for proposing a natural discrete one-parameter polynomial exponential distribution family of distribution by mixing the discrete counterparts of the exponential and the gamma distribution. The probability mass function of the random variable x who follows the natural discrete one-parameter polynomial exponential distribution can be written as the following expression. The distribution can also be written like this, and its corresponding CDF is given by this. In this article, the generalized process capability index due to Mighty et al. 2010 have been considered, which is based on the ratio of the proportion of the specification conformance. Now I come to the point of the section that index for one parameter polynomial exponential distribution. Inference about the CPY is equivalent to that about P is equals to f of u minus f of L. Assuming the OPP distribution, the process yield is given by this expression. In practice, the parameter of the distribution is unknown, therefore it needs estimation. So now let us assume that x1 to xn be a random sample drawn from the PDF of OPP distribution. Then we obtain the maximum likelihood estimate of the parameter theta, which is abbreviated as theta hat, by solving the following equation. Now substituting the value of theta hat in the maximum likelihood estimator of the index, CPY is given by the estimates of the CPY, which is abbreviated as the CPY hat. We have the uniformly minimum variance unbiased estimator of CPY in this expression. I come to the point of the section, index for natural discrete one parameter polynomial exponential distribution. In this case, the index in this underlying distribution, the index CPY is given by the following expression. Like the estimation of OPP, the ML estimates of the index CPY is obtained as below. For given capital T equals to small t, by using the Lemon-Scheffer theorem, the UMVE of CPY is given by the following expression.
Amartya, just interrupting you. Your slides are not moving. Could you please move your slides?
Yes, sir.
Could you please go to the next slide, please?
It is stuck actually.
It is stuck here. Anyway, please continue. Yeah.
So now come to the point of the simulation study. The equation f of x equals to u cannot be explicitly solved in x for the OPP or the ND-OPP distribution without using the Monte Carlo simulation technique for generating the random samples. The fact that the distribution is a mixture of gamma distribution can be used. For OPP or NDPP distribution, the generation of the random samples is made using the following algorithm. Sir, my slides are visible or not?
Your
slide is visible
but
not moving actually.
But
It's
not moving.
I mean, just the first slide is visible. This we can just see your first slide. The title of your talk.
So may I restart or continue?
Put on slideshow.
Yeah.
You can continue, but you can put on slideshow. Maybe you haven't configured.
You just go to the view tab. And from there you can, from there, and in the below also you can. There is a presentation sign. You can go there and.
You see top of your screen, and that you.
I think he has left. Oh, no. Yeah, you can start sharing again.
I mean,
Your sharing is off now. Now it is not visible.
yes, ma'am. I am sharing it from the first. Is it visible now?
Yeah.
Is it visible?
Yes, yes. Visible now.
Yeah. Okay.
Yeah,
Okay.
now
Thank
it
you,
is
sir.
moving, I think. Yeah.
Okay. 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 Now it's moving, na?
Yeah, just move one slide and just move the slide once.
I'm moving it.
Uh,
Is it moving or not?
no.
No,
Initially,
your slide is not moving.
Yeah.
Wait.
So you opened with Chrome, Google Chrome, or any other browser?
Sir, Google Chrome.
Okay, then it should move.
Sir,
share
is
one
it
more?
visible? Sir,
Yes.
is it visible?
Yes, press.
It is visible.
Yeah, press F5 first. Press F5.
Okay, sir.
Okay, manually you can continue. Like from the left bar, you can go to the next slide. Yes, we can see the next slide. Could you please click on the slides? Yeah. Now it's movable. So manually you do it. So from where?
Yes.
Okay.
Yeah. Now continue from where you stop.
Okay, sir. Thank you. So now we come to the point of the simulation study. For OPP or NDOPP distribution, the generations of the random sample x1 to xn is made using the following algorithm. The two distribution, namely the lane-biased Lindley and the Sujata distribution for one OPP family, and one distribution named the natural discrete Lindley from NDOPP family will be considered for illustration purpose. For continuous setup based on the simulation study, we have the UMVV estimator of CPY like this. And for the discrete setup based on the simulation study, we have the UMVV of the estimators. CPY is given by the following expression. Simulation study have been carried out for comparing the estimates of CPY. The bias and the mean square error of the estimates are presented graphically in the following figures. These are the graphs. From the figure 1 and figure 2, it is observed that the bias and the MSEs decrease with the increase of sample sizes, and it ensures that the precision and the consistency property of the estimation of this estimator actually. Now we come to the point of the data analysis. Here we provide the analysis of 3 real-life data set for comparing the performance of the ML estimator and the UMVV of the index CPY. The probability model selection is made based on the AIC criteria, which is abbreviated as below. The minimum is the AIC, better is the model fit. The AIC is calculated first using the ML estimates of the parameters, and the best model is selected. Then the AIC is chosen model is compared with the AIC of the model calculated using the UMVE of the index. Now we come to the point of the real life dataset 1, and here is calculation. We have calculated the ML estimates of theta and the estimates of CPY and its variance and etc. For all these 3 real life dataset, dataset 1, dataset 2, and here is dataset 3. And we also established the expressions of the ML and UMVV estimates of the PMF for the NDOPP family of distribution as are given by respectively. Now we come to the point of the concluding remark. Estimation aspects of generalized process capability index is taken care of in case of quality characteristics following one parameter polynomial exponential distribution and as well natural discrete one parameter polynomial exponential distribution. The MLE and the UMVV are the two estimators compared theoretically through a simulation study and are precise and consistent. Moreover, the UMV of the index performed better than its ML estimator in terms of their MSEs. Some real-life datasets are analyzed and compared in terms of their estimated variance as MSEs cannot be computed in this case. The model selection purpose, the AIC is used. In each case, the ML estimate is preferable. The computations involved in estimating the index are more intensive than those involved in estimating the conventional process capability indices. It perhaps is not a severe concern in the advent of today's computer technology. It is more important to have a generalized index such as CPY covering a broad spectrum of distribution in measuring the process capability, even though it requires a little bit of intensive computation. And this is the references which I have used. And lastly, I must thank all of you. Thank you.
Okay. Thank you, Amartya. Anyone having any question, please can have, you can put your questions now. And, okay, if not, we can thank the speaker.
Okay, thank you.
Yeah, you can.
So may I stop my
yes,
presenting?
Yeah, you can stop presenting.
Okay,
stop sharing. Okay, now we have a special speaker. So now Ovipriya, are you there?
Yes, I'm there.
Okay, so Ovipriya will be speaking on artificial intelligence and few real life applications. So Ovipriya, you can start your presentation. But before Ovipriya starts, let me just take a little time. So he is just studying in class 6, Don Bosco School, Kolkata. So best wishes, Ovipriya, for your talk. So you can start now.
Is my screen visible?
Yes, your screen is perfectly visible.
Good morning, good afternoon, and good evening. My name is Avipriya Adhikari from Don Bosco Park Circles. So the topic of my presentation is artificial intelligence and few real-life applications. So let's start with the very beginning and history of artificial intelligence. The earlier substantial work in the field of artificial intelligence was done in the mid-20th century by Alan Turing. In 1935, Turing described an abstract computing machine. Turing gave quite possibly the earliest public lecture in London in 1947 to mention computer intelligence. And what we want is a machine that can learn from experience. In 1948, he introduced many of the central concepts of AI in a report entitled Intelligent Machinery. However, Turing did not publish this paper, and many of his ideas were later reinvented by others. For instance, one of Turing's original ideas was to train an artificial neurons to perform specific tasks. So, the beginning of modern AI can be traced to classical philosophers' attempt to describe human thinking as a symbolic system. but the field of AI wasn't formally founded until 1956 at a conference at Dartmouth College in Hanover, New Hampshire, where the term artificial intelligence was first coined by John McCarthy. So, what exactly is artificial intelligence? Artificial intelligence, or AI, is the ability of a computer or a robot controlled by a computer to do tasks that are usually done by humans because they require human intelligence and discernment. So, some advantages of artificial intelligence are as follows. AI drives down the time taken to perform a task. AI enables the execution of hitherto complex tasks without significant cost outlays. Artificial intelligence enhances the lifestyle, and artificial intelligence operates 24 into 7 without interruption or breaks and has no downtime. So, we have some drawbacks of artificial intelligence. For example, loss of certain jobs, the implementation cost of AI is very high, AI terrorism, and accelerated hacking. Many people think that artificial intelligence, machine learning, and deep learning are the same because they use the same applications. But artificial intelligence is a science of getting machines to mimic the behavior of humans. And machine learning is a subset of AI that focuses on getting machines to make decisions by feeding them data. A subset of machine learning that uses concept of neural networks to solve complex problems is called deep learning. So we see that artificial intelligence, machine learning, and deep learning are all interconnected fields. Machine learning and deep learning aids artificial intelligence by providing a set of algorithms and neural network to solve data-driven problems. The concept of AI is not only limited to machine learning and deep learning, it also consists of object detection, natural language processing, expert system, and robotics. So as we know that the virtual assistants in our computers and laptops and phones have used artificial intelligence. For example, Siri, which is developed by Apple, Google Assistant from Google, Alexa from Amazon, Cortana from Windows, and Bixby from Samsung. So broadly speaking, the types of artificial intelligence are artificial narrow intelligence, artificial general intelligence, and artificial superintelligence. Now coming to artificial narrow intelligence. So artificial narrow intelligence, or ANI, also known as weak AI, involves applying AI to specific tasks. For example, crawling a web page or playing chess. Or if we take Alexa as an example, if we say, Alexa, turn on the lights, then the processor in Alexa will take the input and give it to the smart light as the output and turn on the lights. Same way, if we say Alexa to play some music, then it will play the music. Few examples of artificial narrow intelligence are face verification at Apple, the autopilot feature at Tesla, the social humanoid robot Sophia built at Hanson Robotics, and the Google Maps. Now we come to artificial general intelligence. Artificial general intelligence, or AGI, also known as strong AI, involves machine that possesses the ability to perform any intellectual task that a human being can. We all have heard about the famous scientist Stephen Hawking. He had once warned us that strong AI would take off on its own and redesign itself at an ever-increasing rate. Humans who are limited by slow biological evolution couldn't compete and would be superseded. Now we come to artificial superintelligence. Artificial superintelligence, also known as ASI, is a term referring to the time when the capability of computers will surpass humans. As we see in movies that the artificial built robots increase their own population and kill human beings. Now we see some real-life applications of artificial intelligence. The JP Morgan's Chase Contract Intelligent platform uses AI machine learning, and image recognition software to analyze legal documents and extract important data points and close it in a matter of seconds. Now, manually reviewing 12,000 agreements takes over 36,000 hours, but AI is able to do it in a matter of seconds. Now, coming to healthcare. IBM is one of the pioneers who had developed AI technology, especially for medicine. More than 230 healthcare organizations worldwide use IBM AI Watson technology. In 2016, IBM Watson AI technology was able to cross-reference 20 million oncology records and correctly diagnose a rare leukemia condition. Now coming to social media platforms such as Facebook. Artificial intelligence is used for face verification, wherein machine learning and deep learning concepts are used to detect facial features and tag your friends. Another such example is Twitter's AI, which is being used to identify hate speech and terroristic languages in tweets. It makes use of machine learning and deep learning and natural language processing to filter out offensive comments. The company discovered and banned 300,000 terrorist-linked accounts, out of which 95% were non-human artificially intelligent machines. Now we have our Google search. When we search, we see many recommendations that AI of Google collects about us, such as our location, age, and other personal details. Now I have this English written paragraph with plenty of mistakes. So I'm going to copy it and paste it in this app called Grammarly.com, which is available in a cloud version and also app version, also in a premium version. So I have copied the text and the wrong ones are underlined with red, and where there is grammatical mistakes, they are underlined with blue. So I click in fix all errors, then it fixes all the errors, and as you can see here I had wrote sometimes. So it suggested a stronger meaning. So we see that the correct paragraph here has detected it with artificial intelligence and natural language processing. So, what technology does this Grammarly uses? So, Grammarly's AI system combines machine learning with a variety of natural language processing approaches. Human language has many levels at which it can be analyzed and processed, from characters and individual words through grammatical structures and sentences, even paragraphs or full text. So we see that there are many advantages of artificial intelligence, also some drawbacks of artificial intelligence. So thank you. Wishing all of you a Merry Christmas and a Happy New Year. So any questions?
So, anyone having any questions, please you can have, and you can ask Avipriyo. And Avipriyo, a very nice presentation. Congratulations and Merry Christmas to you all from my side.
Thank you to Master Ovipriyo for delivering such a nice talk on AI, and Merry Christmas.
Thank you.
Okay, Avipriyo, I don't think anyone have any questions, so you can close your sharing. And we have come to the end of our this technical session. So again, I'm very thankful to Professor Abhishek Adhikari for inviting me to chair this session. So it was a pleasure indeed, and the talk by Avipriyo was indeed an added bonus. So thank you everyone, and wish everyone a very Merry Christmas and New Year ahead. So thanks. So what to you, sir?
Thank you, Dr. Maitri Sen, for chairing this session, and I want to thank all the speakers of this technical session. First technical session of the day it was, and it was really a nice presentation. And as usual, the quite common thing that we have is all the presenters are present in all the sessions. So thank you all. With that, we would like to conclude this session. But as usual, I just want to share few memories with all of you. Before going to the next session, usually when we do it in a physical mode, we usually celebrate the birthday of Lena Trail. So those who have already visited the conference in a physical mode, they must remember that on the third day, we usually, on every year, we celebrate Dr. Lena Trail's birthday. And this year, it would be 80th birthday. So may I congratulate Dr. Lena Trail. Are you there? Dr. Lena Trail, are you here? Okay, if not, then I just share the screen to show you few memories that we had. Is my screen visible?
Yes, yes.
Okay,
Yeah.
so you can see that it was in 2017 at the venue, and Professor Sengupta is today, he is also present here, I guess, and you can see that on that day, he was also there with us. And sorry. Yes, so it was a group photograph. So two of our key persons, Professor Shaha and Professor Odikari, we are missing them a lot. So you can see Oviprio on the lap of Dr. Eric Trell, Bagishadi, and many. So you can see that many familiar faces at the Lena is here. So we all enjoyed. So we are missing all those days as usual. So Professor Dettridge is also here. Professor Dettridge's son is here. So it was like a family get together that usually we do have. So we all miss this, but anyway, hopefully next year we are again going to have this in a physical mode, even in a grand fashion. And of course, we'll certainly miss both Professor Odikari and Professor Shah, Dr. Shaha. So wish you all the best. So with that, may I directly switch to our next session. So we are basically running a little out of time, 7 minutes. So may I now request Dr. Indranil Ghosh to please chair this session. And here we will have 4 speakers, and that would be the last technical session 8. So 4 speaker will be here. I can see Professor Chobe is here. I can see Professor Sengupta is also here. Professor Dettridge is also here. Is Sujitda is present? Professor Sujit Ghosh?
I haven't seen yet.
Okay, I think he will join maybe after some time. Yes.
Yeah.
Okay, so without any further delay, it's my great pleasure to welcome Dr. Indranil Ghosh to chair this session. It's over to you.
Thank you, Dr. Abhishek Odikari. It's my pleasure to be the chair of this technical session 8, and all these speakers, they need no introduction. I'm humbled. These are all stalwarts, as I can consider each one of them. So without further delay, the first speaker is Professor Yogendra Choube from Concordia University, Canada. And he's going to talk about inference on coefficient of variation from inverse Gaussian distribution, some recent developments. Over to you, Professor Choube.
Thank you, Indranil. I'll try to share my slides now, and then we'll start. So, is my slides visible?
Yes.
Okay. So, thank you very much, Abhishek, and Indranil also. This talk is about inference on coefficient of variation from inverse Gaussian distributions. That's the title. Some recent developments basically means I'll be reviewing some recent work from other authors, but there will be quite a few of my work with my colleagues, Devraj Sen and Murari Singh. Devraj Sen has been associated with me for last almost 20 years, I would say. And Dr. Singh has been associated even longer. He's currently, Devraj is of course at Concordia, and Dr. Singh is at University of Toronto. But Dr. Singh was with us in Concordia for 7 years, 8 years on and off. So it's a pleasure to have them also in the audience. Now, I'll just give you a small outline of the talk. So I'll just give introduction, which basically will tell you about coefficient of variation and how we go into inverse Gaussian distribution, because that's the key of this talk. And after some preliminaries, we go into symmetrizing invariance stabilizing transformations, which we worked on a paper on this in 2013. And then talk about hypothesis test, some results. So that's basically review of hypothesis test of CV for inverse Gaussian. Then we go several inverse Gaussian distributions. Basically, the emphasis here is on common CV, and we again use symmetrizing power transformation, and we give simulations. There's some recent work and published in a proceedings of a conference we had in July. Then we talk about Bayesian inference of CV, where we have done some work, and then talk about some further developments. So I go right to introduction. It's very well known that the coefficient of variation is defined as the ratio of standard deviation to mean. And a lot of people don't realize this, but when we go in applied fields, it becomes clear that this is really appropriate when mu is greater than 0. If you take normal distribution, for example, then the sample coefficient of variation, which will be S over X bar, the moments do not exist. One can, unless mu is considered to be positive. And people have made mention of this in applied fields. I will tell you more about why it's used in applied fields. For example, everybody knows signal to noise ratio. That's actually the inverse of coefficient of variation. And it is used in queuing theory, renewal theory, reliability theory. A lot of examples are in a paper by Nairi and Rao, 2003. Also in finance, it is used because it's considered as it's a metric to selecting stock or portfolio with smallest CV. In this case, CV is interpreted as smaller risk, where risk is synonym for variation, and larger rewards is the value of a stock. This is very well described in a finance book, which I read in chapter 18. Agricultural research, which of course Dr. Singh has been has worked a lot. This is used as a measure of field heterogeneity and stability in genotype environment interaction. And there is paper by Dr. Singh and his colleagues in 93 and 2010. So, as I said, even though CV is recommended for non-negative data, its counterpart has been used for inference in normal data. It follows a non-central T distribution actually, and the resulting sampling distribution was investigated a long time ago in 1936. There's some work recently by Jay Kumar Sultan in 2015, but a lot of things have been written about distribution and by Sokol and Ralph. Also, I go back, sorry. Let's go next one. So the distribution is, as I said, is not simple. So there are a lot of approximations. And there is a paper in 2011 which talks about all these approximations. Of course, it is for normal populations. This is actually in the context of computing confidence intervals. However, since it's considered to be really important or meaningful for non-negative support, log normal gamma other distributions have also been considered. I give here some references by Koopmans et al. 64, Pang et al. 2005. What we are going to talk about is the inverse Gaussian distribution today. And this has been really used, found very useful in positive and positively skewed data and the book of Chikara and Folks. And then later on I refer by Seshadri as many examples where it is useful. So first we provide some background and then we go into inference problems. The distribution is, this density is given, which this part looks a little bit like normal, except there is x at the bottom here, where we usually see sigma square. And there is x in this also. So, I mean, it doesn't look very simple distribution, but if you go into Chikara and Folks and Chikara's book, and Folks and Chikara had a 1978 review paper, they have basically a lot of interesting properties mentioned. The distribution function is actually, I do not write here because I have a lot to cover, but it can be written in terms of the distribution function of normal distribution. So computationally, it is not difficult. It has nice structure. Later on, you'll find with this parameterization. Lambda is called dispersion parameter because the variance is mu cube over lambda, and mu is, of course, the mean. So the coefficient of variation is square root of mu over lambda. Many papers actually find to discuss this square of CV, which is mu over lambda, because you can estimate mu over lambda unbiasedly. However, if you take the square root, that's not unbiased. But if you want confidence intervals, etc., one can find confidence interval of the square and convert it into confidence interval of delta. So here is the structure I was talking about. X bar, if you take, it also has IG distribution. Now parameters becomes mu and n lambda. And quantity U, which is associated with reciprocal mean, because 1 over summation 1 over xi, and you take its mean, it will become reciprocal mean, which we denote later on by x bar r. And this has a chi-square distribution. So it's related, it's considered actually some people have named, especially Madholkar and his students have written a lot about it. And they call it fraternal, IG is called fraternal twin of normal distribution. So for the, it's considered as normal distribution is for data on the whole real line. IG distribution is considered to be on the non-negative. So here you see that from this relation 2, item 2 in equation 2, we can find unbiased estimator of 1 over lambda. That's precisely U. And therefore mu hat, which is x bar times U, gives a unbiased estimator of pi, which is the square of CV. And it has a nice representation which can help you in finding exact distribution. Actually, that's what computational we can write down, because Z is the inverse Gaussian and Y is chi, and they are independent. So one can write that as a integral, and that's what we have used later on in our paper. Also, a mean can be very easily written once we have that representation. I'll just skip this, but basically saying that, telling you that means are very easily obtained. Of course, one can find the leading term, which as so leading term here is phi square 2 or due, but we don't need to do approximations at this point. So next we are going to discuss variance stabilizing transformation and symmetrizing transformation. The basic thing I'll just quickly say, I think people know it, so I'll not go in details. This goes back to Bartlett 1947. Basically, one finds a function g of a statistic t, which is asymptotically normal, and expands in a Taylor series, finds the moments and the variance, and equates the variance to be some constant, and then solves the, you get a, I'll show you, get a differential equation, and we solve the differential equation and get the variance stabilizing transformation. So this was actually discussed in 1983 in a joint work with with Professor Madolkar for general statistics like the Bartlett, and 1984 for Fisher's transformation. We showed that in that paper that Fisher transformation is a variance, is a symmetrizing transformation. But in general, it's difficult. I'll give a little bit details what it, how it comes out. But this general variance stabilizing transformation may not be symmetrizing. I mean, usually people use it because you start with normal distribution, so you have stabilized the variance. So asymptotically, it will also be normal, and therefore you can use it, approximate it by normal distribution. And that we call symmetrizing transformation, basically because the third cumulant may be approximately zero. However, there have been other work, those are simpler than the general transformation of solving a differential equation by considering the power family. That's in Hinckley, 1975, 1977. And then people like Hall, they have worked on it. So it's a very interesting applied problem. In the present case, actually, I also show that power transformation is easier to handle and general symmetrizing transformation may be fretted upon due to numerical complexity, as you'll see. So here I give a general, so we start with Tn, which is approximately normal. It depends on a parameter phi, and we want to make the transformation Gtn so that the variance is constant, or it doesn't depend on phi. So basically, we can expand the second mean. For the second mean, we get approximation G prime phi square, 1 plus xi1 phi. Xi1 phi is phi hat expected value of phi hat minus phi. In this case, it is 0 if we have unbiased estimator. So for variance, and the second one is for the third moment of G phi. These are the two expressions. These are approximate in the sense that basically we consider two derivatives, G prime phi, and the terms we assuming that they become negligible. And that's on moment conditions that happens to be true. So once we have that, then we basically take the first mu to phi, and we equate that to constant c. We get the equation, the second derivative G prime phi is c over sigma phi, where sigma phi was the variance of the statistic, sigma square phi variance of the Tn statistic. So you get this is the differential equation one has to solve. For the symmetrizing transformation, we equate G3 phi to be 0. And we get the differential equation like this, which is a little bit more complicated. We have to solve basically two integral equations. One is 16, and then we substitute in 15. So it has to be done numerically. These equations missing, but basically you have all the moments. Once we know the moments, we can solve these equations. In case of variance stabilizing transformation, we can solve exactly. And in this paper in 2017, we use this. For the symmetrizing transformation, we have to use a numerical solution. In the normal case, we integrate 0 to x, the quantity what we had here, e to the power minus w phi. Of course, it's a function of phi, but in general, this is what we call the integral representation. So, basically, we have to solve this integral equation numerically. For the case of distribution, inverse Gaussian distribution, we actually cannot integrate from 0 because SU in that case is diverges. And so we integrate from 1 to x. So it differs from some other constant from Sx. So this was used in the paper in 2017. Now, I talk about symmetrizing transformation. That's very simple. What one does is, if you say statistic T and divide by its cumulant K1, or for mean to the power H, this will approximately have this moment. And chi, etc. are given before, or these are the ratios of the cumulants. So like chi 3 is K3 over K1 cube, chi 2 square is K2 over K1 square, etc. Psi 2 is K2 over K1 square, etc. And moments of, other moments, like if you are take R equal to 2, 3, 4, etc., you want other moments. So basically, you want the third moment of this, and then we equate that to 0. So that's given in the next one. So this is mu 2h, mu 3h, mu 4h. If you equate mu 3h equal to 0, we get the equation 29, h naught 1 minus k1, k3 or k2 square. So if we know the moments of the statistic T, we can find this. And this looks very simple, but the finds that this approximation is very powerful. So in this case, we will take T equal to nu phi hat or phi. So K1 is nu from the expressions I gave you. K2 is 31, K3 is, it's all computable in terms of nu and phi. And so if you want to do a test, then which depends on phi hat, actually I'll just mention later on, phi hat is considered to be found to be uniformly most powerful for the at least one-sided alternatives. I'll just mention it here, but give the details a little bit later. So the test depends on phi hat. It can be made for finding p-values or test statistic by this normalizing transformation. Because what we do is substitute the null value of phi in finding h naught. So here is the z statistic. Now, I said this will be relevant in hypothesis testing context. 1972, actually Chikara's, that was thesis, he mentioned about likelihood ratio tests and so on, and suggested large sample approximations. But she found those large sample approximations were not really good for practical use, and suggested exact distribution. He has some, basically, exact distribution can be written in terms of the statistic Z and chi-square, which I have explained before. And this we used in 2000 paper to provide some approximations and comparing approximations. I'll just show you. So the approximations here are 4 approximations. I'm talking about the statistic. One can do a IG approximation and a gamma approximation. However, one finds that if we mix these two approximations, these are moment approximations. We know we equate moments. Then we get mixture approximation. So we compared this for different phi's. Usually 5.1 is, this is 10%, and 30% is considered actually big. 10% of coefficient of variation. It's measured in percentages. So we choose that, and you can see if you compare the first one and the last one in for each column, first value exact and the last value, they come very close. And we had graphs also, but I'm not presenting here. The error is very small for distribution functions also. So this approximation for practical use is very good. Now, we talked about power or symmetrizing transformation. Actually, that we considered later on. And that symmetrizing transformation and the mixture transformation comes out to be almost same. Therefore, we'll prefer the power transformation for approximations. So we are considering now K IG populations, and the basic purpose here is actually to test hypothesis if all these coefficient of variations are equal. And the second one, if they are equal, if they have common value, what that common value is, can we test it? So in this case, we can say NI observations, KIG populations, and we have unbiased estimators and ML estimators of mu I and phi I, and that can be combined into getting estimators of mu I and a common coefficient of variation phi. So that's the next. These results, of course, come very easily, and phi I hat in this case is maximum likelihood, but we can use unbiased estimators also, which will be Ni minus 1 over Ni times MLE. So first estimator we consider is simple mean of the MLEs, and that comes out to, as you can see, N minus K over N times 5, which is not unbiased, but can be made unbiased just by simple scaling correction. And variance phi hat E1 can be also written easily because it becomes a linear function. Maximum likelihood estimator is a little bit tedious. There's no explicit form, as you can see in this equation. Phi hat is on both sides, but it can be solved numerically. We suggest that we take that first iteration, call it phi naught hat, as phi hat E1, phi tilde E1, and solve numerically. We can solve it by univariate uniroot function in R. Actually, however, if you use Newton's method, it is like this. And finally, we get we can write G and G prime, this G and derivative G prime. And until we get convergence, we get finally this MLE, which we denote by phi hat. Large sample variance of this can be obtained by information matrix, which requires a little bit work, but its inversion is easy. Well, that's the theorem. We basically need the large sample variance for testing. And the third estimator we take, actually it's unbiased. So we take phi I hat here is unbiased estimator, and we take Ni phi I hat over N, and that's phi 3 hat. Its variance also can be easily obtained. This last estimator is something which actually we found to be more useful. It is something like we take linear estimator combining phi I hat and find its minimum variance. In that class, the weights will be minimum variance unbiased weights will be here it will be phi I and phi I, but for estimating, we need WI to be depending on phi I hat. So the variance also can be easily obtained, which is below. Indranil, please tell me the time.
Yes, Professor Cho, we have 5 more minutes left.
Okay, because we started a little bit late. So, so anyways, likelihood ratio test we have used. So all these computationally. Then we also used test based on weighted sum of squares. We consider so 4 statistics based on the 4 estimators, simply using them as normally distributed. And asymptotically they are, and their variances can be estimated. We have the 5th estimator where we, for testing common, we can find the mean and variance by replacing phi by phi naught. However, in the WIs, etc., we use phi I hat, and in cumulants also can be obtained. So mu prime 1 H naught and mu 2 H naught can be obtained, and the approximation which we talked about can be obtained for phi at E4. Now, this we'll call Z5, but we have another one, Z6, where all the phi I hats have been replaced by phi naught. There has been a numerical simulation to compare these, their p-values and their performances. I basically represent here p-values, performances. I'll just tell you that the last estimator, Z6, comes out to be on the top in terms of MSE. Okay, here I give you this table, which you can just look at the last 2 columns. So you can see that Z5 doesn't quite catch up the type 1 error rate. However, Z6 really comes very close in all the cases we considered. And this is the power of power symmetrizing transformation. So Z6 is really a kind of improvement over Z5. And we have not investigated, but other phi hats could also be symmetrized in a similar way. But since phi hat E4 comes out to be the best estimator, we have not really worked on symmetrizing others. So for the little time, whatever we have left, I'll summarize the Bayesian inference we have worked on. Bayesian inference, generally, most of the papers which, I mean, there have been work, I don't go in detail, is mostly on the phi, not delta. But if you want Bayesian inference for delta or the coefficient of variation, then we have the prior on delta, etc. And gamma prior has been considered, log normal prior have been considered. They all require numerical solutions. So if we are doing numerical solutions, we thought that we can consider more flexible prior, and we consider what is called generalized inverse Gaussian. As you can see that this is very similar. For the case of this is a generalization of inverse Gaussian, because the power in inverse Gaussian is Q is equal to 1/2 actually here. So if you have instead of 1/2, you have some other power Q. Of course, the things then become complicated numerically. They come in terms of what is called modified Bessel function of second kind of order Q. That's written at the bottom. But the computations of this is very much available these days in R and other software. And this is very well behaved function. So we consider this GIG, and we consider, I want to show you the flexibility of GIG, these kind of distributions it can generate by taking different, I mean, this is actually is the exponential distribution. And you can get something, of course, inverse Gaussian is a part of it, but then you take others, you'll get other shapes. You can get closer to shorter tails or longer tails. Likelihood is easily obtained in terms of maximum likelihood estimator and of mu and delta. So if you want non-informative prior, of course, you have to do Jeffreys prior, and in this case, actually, Jeffreys prior exists. This is found in 40. In the paper of 1979, actually, Jeffreys prior, if we have parameterized in terms of psi and lambda, it doesn't exist. So it's a nice expression there, and you can find the posterior. You can find the posterior mu. Of course, we are not that much interested in posterior of mu, but we are interested in the delta. This can be written explicitly, except for a constant, and people who do Bayesian computations, the knowledge of constant is not important, and then it can be computed by numerical integration basically. But we can do Gibbs sampling because we get more complicated expressions that I see for informative prior later on. So later on we did some computations which I'll show you. In this case shows that, I mean, one doesn't need to go find an exact normalizing constant. Instead, you can do Gibbs sampling. It gives important results. So I'll just summarize that we have considered for informative priors, again, GIG prior, generalized inverse Gaussian for both mu and delta. And posterior distribution of both mu and delta is obtained except for a constant. There is something interesting that if you do a sort of large sample analysis, we find that for large, I'll just show you here, for large n, one can get the posterior, like in 52, which one recognizes GIG distribution. So one can say that GIG is a conjugate prior for delta square, for large samples at least. I'll skip the posterior distribution of mu, it's similar. It can also be computed, which is not very, it doesn't give a very informative result, but just wanted to see what it comes out to be. Now, other one we consider cases, possibilities that mu we consider GIG, and for delta we consider gamma prior, that has been considered in literature. But we consider the gamma prior of delta given mu, because this makes more sense in applied problems, because delta is really defined in terms of mu and sigma. So this comes as a inverse gamma prior, and this again can be analyzed, and we get a little bit complications, but I'll also give you for large X, the posterior distribution of mu is again a little bit complicated. For mu, again, it doesn't give any known distribution. But so I'll show you now that for this example, this is a very standard example used for this kind of Bayesian inference. Many cases, this is exact posterior obtained by numerical integration, and we use a algorithm which is, I think since we don't have much time, numerically we basically take, we have to find two values for highest posterior density, so that the probability to the lower is so that probability of that interval is 1 minus alpha. But highest posterior density means we have to solve a equation like this, that the delta L delta U is the interval, probability between delta L delta U is 1 minus alpha, and the ordinates at delta L delta U are equal. So basically we solve equation like this, k between 0 to 1, we take the mode, and we basically cut horizontal lines that basically gives you this equation. So we find from 0 to delta L probability. Delta L is between 0 to delta M, I'm sorry, and delta U is between delta M to infinity. But you can solve this equation numerically, and once we find that K, then that gives me the value delta L and delta U. So a variety of parameters are chosen, and you can see here now I just present the simulated computation and exact computations. So basically, I think finally one can compare the HPD interval, mean and mode, etc., are very similar. For all these cases, we have very many variety of parameters, Q and A and B and alpha and beta. So I'll take just say that what we are trying to do next is basically work on, there have been work on this, on inference on common coefficient of variation. That is actually, I mentioned this paper is just we described, and which is very similar to the work for normal case in 2000 by Fork. Tian has done something which is called generalized variables, based on generalized variables of Virahandi. And Kang has attempted to develop first and second order probability matching priors for the case of common sieve in 2008. He says that second order probability matching prior does not exist. It turns out that one at a time and two group reference prior satisfy the first order matching criteria, but Jeffrey's prior does not. So these things we are going to discuss, and maybe something similar what we have based on GIG prior. We are working on common coefficient of variation problem. Anyway, I'd like to thank, acknowledge the support from our grant, from my grant. He also mentioned that this work we dedicate, this talk we dedicate to memory of Professor M.R. Adhikari, which I'll miss him a lot, but will cherish his memory. And thanks again for everyone who is listening, and take care. I think that's all.
Thank you, Professor Chobe, for a nice and interesting talk. For the interest of time, I will request if the audience have any questions, send email to Professor Chobe. So thank you again. Moving on, now we have the Professor Ashish Sengupta, and he holds several different positions at Indian Statistical Institute, Augusta University, USA, including Middle East Technical University in Ankara, Turkey. And he's going to talk about testing homogeneity of mean directions of several distributions on manifolds. Over to you, Professor Sengupta.
Thank you, Indranil. So let me share my screen. Okay, so let me see. Can you see my screen coming up?
Yes, now it is
supposed to come, right?
Yes, it's not visible, but it says not yet.
Sir, the screen is presenting, but you need to open the presentation now.
Presentation.
Yeah, but the screen should show up first, right?
You need to open your presentation now. You minimize the browser window.
Okay, can you see my screen now?
Yeah, now it's visible.
Now it is visible.
Okay, so let me try to maximize it. So
please click on the slideshow and it should work fine.
I don't want to do the slideshow. I just want to go to the. Okay. Will this work if I maximize from my? Can you see it now?
Yes.
Yes.
It is full screen, right?
Yes.
Okay. All right. So, okay. Thank you, Indranil. Thanks also, Abhishek. It's a pleasure to be talking in this conference. Of course, at the very outset, I should say that I miss Professor Adhikari very dearly, and my homage, my respects go to his memory. And as Yogen also said, I mean, I would like to dedicate this talk in his memory too. Indranil, can you tell me how much time I have?
Professor, you can go ahead. I mean, like.
No, I mean, 30 minutes. We are originally scheduled for 30 minutes. Do you have 30 minutes?
I guess I might slowly ask.
Let me go ahead.
Is it okay? Because the first.
Okay. You just let me know 5 minutes before my.
Okay, I will.
Good. Okay, so this talk is based on the homogeneity of mean directions. Those of us who are in statistics and those also are in mathematics with a statistics course in the BSc, even in a single course, you must have seen the testing of hypothesis and analysis of variance. So that's the basic testing or inference problem that we all grow up with, where we would like to compare the means of several different populations. In particular, we are familiar with the analysis of variance ANOVA, which is for the equality or homogeneity of means for several independent normal populations. Now, from our school days, of course, we have come a long way, and we are now facing various types of data. There have been several generalizations in need for coming up with tests for homogeneity, not only for the data on R1, but also not in the Euclidean manifold only, but on different types of manifolds. So my talk is based towards that, an attempt to try to generalize the analysis of variance to the case of data on other manifolds beyond the Euclidean one. So I call it ANOSMED in the general analysis of spherical mean direction. Let's see if you can reach that far. But definitely, we'll go through the analysis of mean directions for circular distribution, which is by itself a manifold on S1. So, okay. So, as an introduction, there are many diverse scientific fields where we come across this kind of circular data. For example, in biology, we look at the direction of flights. We measure the angles in which the birds are taking off. In geology, Earth's magnetic pole. In astrophysics, the arrival directions of showers of cosmic rays. Meteorology, wind direction, and so on and so forth. And of course, in medicine, these are related to the what we call our human body rhythmic activities or circadian rhythms. So as an introduction, if you look into a more mathematical way of the data, so it will be measured in terms of angles or directions through compass protectors. So this will be definitely angles. And then we also
Professor Sengu, your voice is breaking.
Data. Further, if you look into transformations like that, we want to go, yeah. Can you hear me now? I mean, I can't do much.
It is clear now.
Because it's because of the connection. In fact, when I was listening to the previous talk, the connection is going on and off. So this erratic nature, maybe you have to survive with it. Anyway, so now let me get back. So once the initial zero direction is fixed, then the circular observation can be uniquely represented. Why is the initial zero direction so important? Because on the circle, it is the data that you look at, the distribution will be invariant with respect to rotation. So whatever zero you take, the shape of the distribution will still look the same. And in measurements, for example, mathematicians take zero as the due east. People in physics will take north as the zero direction, and people in geology will take the south as the due south as the zero. So there are various types of definitions of zero. So we need to fix what is the zero direction. And then there will be the clockwise or anti-clockwise way of measuring. So that is another aspect. So we need to fix which direction we are measuring in. And finally, when we talk about direction, it could be incoming or outgoing. Like when you look at the bird directions flying out, so it is the outward direction in which the birds are flying. And when you look at the wind direction, it is the direction from which the wind is coming in. So this is the inward direction. So there's a lot of this kind of measurement directions that we need to look at. And once these are fixed, the data needs to be invariant with respect to this direction, and our tests accordingly, or the inference has to be accordingly developed. So directional data in general, they consist of multivariate observations with components being linear, circular, axial, and so on and so forth. And we can have a hypertorus, the S1 cross to the power P, or hypersphere, which is SP, or axial distribution, which is on the axis, and hypercylinder, SP cross RQ. So these are the observations on different types of manifolds. So these are the examples of smooth manifolds, but we could also look at disks and hyperdisks, where we could have some other complexities too. Now, the initiating references are these books. This book is supposed to come up, hopefully in 2022, sometimes in the middle or early 2022. And this is another book on rather a series of papers are here. So those of you are interested in this area, lots of fascinating applications, good theory. There are about 25 chapters, and you'll get a wealth of information from here. And finally, this 2001 book is a basic book on study inference for circular data. So this is the first point when we try to look at directional circular data, how they differ from linear data. So if you take the two angles, like 20 degrees and 340 degrees, two birds are flying out in two directions, 20 degrees and 340 degrees. Then if you take the arithmetic mean, what is the average angle, then you will get, for example, the arithmetic mean is 180 degrees, which is nonsensical. And hence, obviously, you cannot use this measure. You need to use some other types of mean, which is your y bar equal to 0 degrees, which is with due east. And that is nothing but a mean, which is also the trigonometric mean that corresponds to the direction of the resultant that you are looking at. So as soon as we notice that even the mean does not really tally with our mean on the real line, naturally the inference procedures will definitely differ as we go along. So we'll need different statistics to measure the mean, the variance, the correlation, and obviously different statistics to test hypotheses, different types of hypotheses. So the density function for a circular unknown variable, the first two are quite common. Expected is a non-negative, and integration should be equal to 1 over the content. And then finally, the third one is comes out because we know that over here, the theta plus 2k pi is equal to theta for any integer k. And because of this, naturally, the density function should also be the same. So in other words, the f to be a density function must be periodic also, 2 pi periodic, in addition to satisfying 1 and 2 above. Okay. So we are trying to look at the problem of analysis of variance, and which is the generalized to which we call anomet. So we're observing theta ij's, independent observations from circular normal populations, and the problem is to test mu1 equal to mu p, all independent populations versus at least one inequality. No reasonable test exists for anomet under small concentration. If it's small concentration, that means that the opposite to it is we are going to have the variance is going to be large. And each group is small, n1, n2, nk are small in number. So the value. So this is the situation which are most often encountered in practice, and there has been no test developed for this situation. As we'll see why, as we go along, I'll explain why it is. So our aim is to derive an universal and efficient test, universal in the sense that it will be able to capture the situations of small concentration or large variance, that is large noise, more unreliable data. So that's where large variance, that's what we're going to look at. And also the small group sizes where the efficiency of the test really gets hurt because of the asymptotic spelling there. So we are trying to develop some tests which will take care of this situation. And finally, we're going to generalize to cover situations with not only symmetric data as in the normal case, but also to the asymmetric one, multimodal, and then related to other manifold on the sphere, etc. Okay, so if you look at mu as the mean direction, the first point that we see that the difference of the mean of the angular differences is not the same as the angular difference of the means. So if you look at two means and take the difference, theta 1, theta 2, theta n, phi 1, phi 2, phi say m, and if you take theta bar minus phi bar, it is not the same as looking at the mean of the summation theta I minus mu I. Mu I minus phi I. So this relation doesn't hold as in the linear case. So immediately we need to look at some other statistics rather than x bar 1 minus x bar 2. So what kind of statistics can we take? Can we take alpha minus beta? Definitely not. Sin alpha minus sin beta, because looking only at sine is not make any much difference, because as you know, sine of alpha is the same as going to be equal to sine of alpha plus pi, and over there, if you look at the conditions minus pi, they will be the same again. So that difference will not also work. So some type of differences is necessary. What would be a right measure of the difference here? So to derive an ad hoc test, that is what we have to keep in mind. So what would be a proper measure of difference? Maybe the arc measure on the circle would be one measure, or other types of measure as you will see as you go along. So there's a multiple testing problems are there, and then LMP, large sample problems, all kinds of problems will come along if we could know what is the nuisance parameters are known. So the motivating example I want to start with is the one that that we have in our conference here, the session with the health sciences. So here's an epidemic disease, the spread of epidemic disease. It's called acute primary angle closure glaucoma, APSCG. And we would like to know whether this APSCG, they are really affect the patients because of the environmental conditions. And there's a lot of study on that. The amount of sunlight, environmental conditions, they do seem to affect the human beings. And it could also be because of their age, also because of the sex, and other types of the variables that are involved in the measurement. So here is a clear case of looking at the testing for the effect of the time at which this disease occurs in different groups. Is this the same time, or do they differ depending on the groups, depending on the environment, and so on and so forth? So here, there's no angle, but we look at the day as a 360 or 365 degrees. 365 days correspond to 360 degrees. One day correspond to 0.986 degree, and this is how we transform the data. So you can think of COVID-19 as a possible application. You can think of whether it has been homogeneous with respect to the seasons, the attack of COVID-19, or it has been homogeneous with respect to the different types of the age groups, or maybe the sex. And what we mean by the effect, it is the peak time. So does it affect the individuals more during the winter, or more during the summer, or more during the spring, and so on and so forth. So this is another application, but good application of this has been given by Gao in Statistics in Medicine 2006. It's one of the real life data, which will come to later on. So now the setup is here we have independent circular normal populations. The F theta ij, you look at there is a circular normal density, is also called the von Mises density. And over here, the kappa plays the role of the inverse of the deviation, it's the concentration parameter. And mu I is the mean of the I population, mean direction rather. Okay. So with this setup, we want to find out how to compute the mean. Look at the mean direction, theta I dot is taken as the arc tan of SI over CI. So it's the sum of the sines over the sum of the cosines and the tangent specific or quadrant specific value of the mean that we look at, and this is how we define the mean direction. So the MLE of kappa comes out as a solution of A kappa equal to R bar over summation Ri over N, which is R bar. And due to the monotonicity of A kappa, this is uniquely obtained. So there's no problem in getting numerically a solution of kappa hat. The multi-parameter testing problem can happen with or without the presence of non-location scale nuisance parameters. Now, if you know the values of the nuisance parameter kappa, then one can formulate the LMMPU, which is going to be the used of the JASA paper, and we have developed the test for the ANOVA with a known variance. In this case, the similar application can be done if kappa is known, or the kappas are known. Our aim is, of course, to get universal efficient test of homogeneity of the circular means direction. So ANOVA to ANOMET, we come back again, and this is the problem formulated. Their references are these two papers. So recent papers are 2020 Academia Sinica, 2020 International Review. This is a joint work by one of my former ISI students, Kulkarni, and you can get both these papers. The second one is still in the DOI form. Probably it has not been available, but I can send you if you're interested. The existing methods are Watson-Williams. As you see, this test is developed using the normal approximation of the von Mises under the assumption of large kappa. So that don't get fooled by the expression that it's a F statistic. It is not because of the large N. It is because of the large kappa, that is large concentration. That is, all the observations are measured with high precision. Okay, so there's a very little variability in the observation. But that is rarely the case in practice. And unlike the F approximation that we use Cochrane's theorem by looking at the orthogonality of the chi-square, and where in many cases we take the normal approximation by taking n large. Here it is not n large, but it is the kappa that is needed to be large, which is rarely the situation in practice. So these tests have not been really quite helpful or popular in practice. So I'm not going into the details. So there are other tests, likelihood ratio test, which also suffers a similar problem. The level alpha or the significance level that you look at, the size of the test drastically goes down, and hence these tests do not perform well in practice. Now, why is so? This is because that we are, the first one, as I said, is under small concentration. Second one is small group sizes and small concentration again. So this is really coming up because of the complexity in the distribution arising of kappa being not a location scale parameter. This parameter is non-scale parameter. So there are some booster approach, approach, and a parallel comparison approach. They do work in certain ranges of the parameter space, but these are not universally accepted. So what we try to do is to try to use the integrated likelihood approach. And this integrated is a novel approach where we do not need the nuisance parameter to be a parameter location scale invariant parameter, but it can be any real parameter, okay, or even a vector value parameter. So the nuisance parameter that we're looking at is can be real or vector value. So the interesting part, the lambda that we have is a nuisance parameter such that psi and lambda should be orthogonal, the parametrically orthogonal. This is the part that we need. So once we have that, then we can look at the marginal likelihood, conditional profile likelihood, etc. So there have been quite some work in this area. And these advantages, they are always available. They lead to asymptotically efficient inference. And in many cases, they outperform method based on the profile likelihood. Now look at the pi lambda site. It's not a Bayesian one. We are using what we call a weight density. It looks like a pi density to wipe out the lambda, the nuisance parameter. Okay, but choosing this is a problem. So this was first proposed by Karlfish and Scott, and later there's a series of papers in Biometrica, GRS, statistical science, and so on, and mostly related to various types of distributions. And as I mentioned, the prior has to be chosen in a suitable way to ensure good properties. And of course, we have a parameter of interest is to be real valued. It's the scalar one, not vector. In our case, unfortunately, we have the bullet is a multiple vector parameter of interest, and so readiness result do not apply. So we want to generalize this, and to do that, the success of our approach depends on the orthogonality between the parameters of interest and nuisance parameters. We want the Laplace approximation amenability, the choice of the weight function, and ILRT minus profile likelihood should be OP of 1 over n. And finally, we use the tuning factor to achieve the size of the test and increase the efficiency of our test. So the chi-square approximation of profile requires the parameter space to be open. If you use the LRT test, this will not happen because our parameter space is semi-open. And observe that mu is from greater than equal to 0 to 2 pi. So it is on one side, it is closed. And hence, it can be, the test can be on the boundary. The usual chi-square approximation will not work there. The difficulties of this then is the construction of weight function, derivatives of the constant, constant, that actually is usually unknown, and the non-nullity of the expected of the Q of this port function, which is often not so, for symmetric directional distributions. Derivation of the proposed. If you look at the derivation of the likelihood ratio test, ILRT, so we look, here is our joint likelihood function, and then we take the weight function pi kappa. To start off with the simplicity, I took n, the power n. We'll modify that as you go along. And we take the n, and then this is the likelihood function. Then it becomes proportional to L alpha theta. You take an L with pi, multiply with pi, integrate out the nuisance parameter, and the resulting the function that you look at is L alpha theta. And this is the one that we'll be using for our likelihood ratio test. So it is the integrated likelihood ratio test that will be based on this particular likelihood function. As usual, we'll take the under H0 and under H1, the parameters to be estimated, and the nuisance parameters will be estimated under H0, H1. It's not difficult. It comes in the same way as I showed you in the earlier one. The pooled observation in the case of equality, and individual means in the case of under H1. So the L function, it works out over here. You take the lambda bar. This is the notation is to make you aware that it's integrated likelihood ratio test. And so you take the usual supreme under theta naught and theta 1. And if you take this, it comes out as n minus 1 over 2. So n minus 1 over 2 is the one is a factor that is coming up over here. And this is a magic quantity. If we chose it, why we choose it, we are going to show you later on. In fact, we can take this as an, as a note over here. Please read an as a subscript n, and then use this an. A similar test case can be derived, and it has a similar form with a 2an log of that quantity. You note that it is exactly the same except n minus 1 replaced by an. So what is the role of an? This an is a tuning factor. So we will use this an in such a way, depending on the kappa, which is unknown to us, p, and the sample, the group sizes. If we assume that they're all equal, then it will be easier to work out, to find out what the an is. This tuning factor will be obtained in a way so that we can get the size of the test and also increase the efficiency of the test. The theorem is asymptotic distribution of TRLT is chi-square p minus 1.
Sir, Sengupta, sorry to interrupt you. You have 3 more minutes.
Go ahead.
You have 3 more minutes, Professor Sengupta.
Okay, I'll try my best. Okay. I'll try my best, okay? So all right. Now, if you look at this distribution theory, so here the orthogonality of the parameters hold good, number one. And secondly, the approach that you said, if you expand the Laplace approximation can be used because of the exponential nature of our distribution of the test statistics that you're looking at. And finally, the approximation, the OP that we look at, the profile likelihood, over here, we know that the profile, the difference of the likelihood minus the profile likelihood asymptotically goes to a chi-square distribution. These 3 things together will lead to the chi-square distribution. The unequal case has been also considered, and I'm going to, because of lack of time, I'll just skip through, but it is also a chi-square p minus 1 distribution too, okay? So the performance over here is shown by this graph. You see that the ILRT outperforms all the known tests in a good way, and even for our target areas of small kappa and small sample sizes, group size. So here is an example where it works, again, for a bimodal asymmetric distribution. It also works for a situation of the Papa-Constantino, which is a distribution where you can have flat top and highly peaked. I'll give you a real life application to end up with. The real life, the Gauss data that he gave. So the data set is extracted from the database. There are groups over here, 4 groups, age below 50, 50 to 59, 60 to 60, and above 70. And the table that we have, the estimated concentration that is very small. You see, this is a difficult place. This is where the difficulty comes in. And the group sizes are not large. The total sample size only is 132. So following the recommendation, we find that the ILRT is the most reliable one. ILRT clearly rejects the hypothesis of no difference. The p-value is 0.01. As did the next favored one. And this indicates that the seasonal impact varies among the age groups, that the mean dates of the onset do differ from age to age. So the young children may be having a different time of onset compared to the older people for the case of our ACTP. The strength at which the WW and LRT rejected the hypothesis is untrustworthy because, again, the problem is they do not maintain our level of the size of the test. So whatever inference you are making can be grossly incorrect, leading to hazardous inferences. For example, in the case of cerebral palsy, where in gait analysis, even a small angle difference can make a whole lot of difference in the condition of the patient. The similar hypothesis for the female patients, it showed that they are not really the value that is 0.03, conforming to the tendency of false alarms under some small concentration. So if you take the WW, it gives you a false alarm, you better not use that particular test. In this case, our ILRT again gives you a good result and which is consistent with the understanding. So in conclusion, males are prone to age-dependent seasonal effects, whereas seasonal influence does not depend on age for females. So this was possible due to this MANOVA. If you do a regression analysis, this did not come out because of the interaction between the season and the different types of groups. So I have last 1 minute. I'll just show you that it is possible to do this test for data on the sphere and hypersphere. So again, going to that, we look at the distribution over here, which is the distribution called the von Mises-Fisher distribution on the hypersphere. If you take a p-dimensional one, or if you take p equal to 2, then it's a distribution on the sphere. Similar methods apply, and again, you can find out the values of the test statistics, and it is, again, we can show it is minus 2 log lambda is chi-square. So there's a lot of much more work here, and this is called ANOSMED. I do not want to go through the details of the derivation, but it gives you finally a chi-square test. So the final, I'm skipping to the derivations, the final one is the adjustment value. So how do I adjust? The adjustment factors AN are obtained through some regressions based on the N, the Pn1, the P is the size of the dimension in the sphere that you're looking at, and kappa is the unknown parameter value, which is estimated by kappa hat naught under H naught. So running a particular regression example, with the various values, we come up with a chart what the AD value should be and the BD value should be in the next table that's given here. That gives us the clue what should be the tuning factor. We do not need the tuning factor in the case of circles. In the case of spheres, as you go to higher and higher dimension, this tuning factor can give us greater weights. So I'll skip the examples. And the concluding remarks, this enables uniformly good performance over ANOBED, and it can be used for both symmetric, asymmetric, multimodal, spherical data, and so on. Here are some references. Finally, thank you. We wish you all a very happy holiday season and New Year 2022. Okay, and again, with my respects to Professor Adhikari, I try to end this session. Thank you very much.
Thank you, Professor.
Over to you, Indranil.
Thank you, Professor Sengupta, for such an interesting talk on directional data. I know you've done a lot of work. So for the interest of time, I will request the audience if they have any questions to ask later on or send you an email. So moving over to our next speaker, Professor Dietrich von Riesen is a visiting professor at Linköping University Department of Mathematics and a professor at Swedish University of Agricultural Sciences at the Department of Energy and Technology. And Professor Rosen is going to talk about reduced rank regression in multivariate models. Over to you, Professor Rosen.
Okay, thank you very much. But now I have to upload the talk in some way, which my memory doesn't know how to do. And where Yes, there are a number of buttons.
Yes, just have a look at this arrow within a box.
Yes.
Yes, click on it.
Yeah, I thought it should work, but it just say
Your interest.
okay.
Yeah, your
Yeah, wait, it's on the way now. No, I just have to find it again. It will come. Bum, bum, bum. This.
Does it say your entire screen?
No, it's on my problem that I have to find among 20 screens or 50 screens where the presentation is, which is of course a bit silly. Completely silly, or it's on the other screen. No. It will come. Ridiculous. Here. Okay. I hope you see it now.
Not yet.
Not yet.
Yes,
you don't.
Yes, it's coming.
Yes, it is coming.
You can see it now?
Yes, Professor.
And it moves also. Okay.
Yeah.
Anyway, then we start. So
you can start, Professor.
Yes. Thank you very much, and thank you very much for inviting me again. Of course, it's a virtual session, but I really like the environment, I must say, and also listen to some talks, a mixture of talks, or the mix of talks, and also the mix of age, which I think is very important, from young to the very old. This is how life is a bit. Also, yeah, so let's start here now. Now I'm going to some kind of favorite topics, and this is linear models or multivariate models. Sometimes I will call them bilinear models. And today I will talk about when we have rank restrictions on parameters. So I'm aware of that not everyone is statistician here in this meeting, so I will introduce you to the model relatively quickly, and then later we should look at the rank restrictions. I'm going to talk about the growth curve model, and then it's a main part of the talk. And then we talk a bit about the extended growth curve models, and then we go over the reduced rank regression, and this is in this case on the mean. I will give you some details. And if there's some time over, we should see when there are rank restrictions on the mean and dispersion matrix simultaneously. And in some way, this last point is pretty interesting for, I would say, how we look upon statistics in the future when we have, say, a lot of dependent variables, so high dimensional analysis. Then one can use this technique here. But let's start with the growth curve model. So here they grow, and you will see a lot of matrices. So here we have an observation matrix, or to be strict, the random variables corresponding to the observations. And we have three matrices, A, B, and C. A and C are known matrices. C is between individuals design matrix, like in analysis of variance or in a MANOVA, where you specify, say, treatment groups, for example. A is something which models the structures of repeated measurements. So if you see, we have P repeated measurements, or P variables which are connected. And A models the relation. The growth curve comes if you have, say, growth over time, P time points, and then you model the growth with the A matrix. And this is once again a linear model. And now we look at the standard situation when we have a normal error term. And it means we will have independent columns. And then within each column, there will be an unknown covariance structure. and completely unknown besides symmetric, and we denote that here sigma, and sigma is a positive definite covariance matrix now in the beginning. And this model is in some way of principal interest, I would say, and both theoretical and practically. And from a theoretical point of view, this is the model doesn't belong to the exponential family. It belongs to the curved exponential family, which is pretty different. And at the same time, in this model, and I will show you, we can find explicit estimators of B, the unknown parameters, and sigma. So let's start there. So we start with the likelihood, which is proportional here, and here we use the normal density. And so we have the unknown B and an unknown sigma, and we want to find the maximum. And one way of doing it is just for fun, maybe it's more strict to use some inequalities, because this we should use anyhow, but now I have differentiated the likelihood. And if I'm differentiating with respect to B, I will get this expression. If I differentiate with respect to sigma inverse, it's easier because you have a linear function here. And do some calculation because there's a symmetry in sigma, which one has to take into account. Then we get an equation of this type, that the n, the number of observations, times sigma equals this quadratic form. So what you can see here now is that this is a very non-linear equation. So we have sigma here, we have B, and in sigma we have B also. So then we see that it's a bit amazing that we can solve this explicitly, and we can do it in a simple case. Otherwise, we could think about that we have to iterate the solution, but this is definitely not necessary. So the trick is that if you start with the first equation here, we have it here. This can be rewritten using a projection here. This is an idempotent matrix. So these two is not just implies, it's in fact they are equivalent. So instead of solving this equation, we solve this equation here. And why do it? We can see it from the next equation. We can reformulate sigma here, or this equation here, as a sum of two quadratic forms. And here's a sums of squares matrix, which I will define later. And the important thing is that the S here doesn't depend on B or any sigma. So this is independent of the parameters, and then we have this part here. So we have this equation and we have this equation here. What we are doing now is to pre-multiply it with A transpose sigma inverse. If we do pre-multiply here with A transpose sigma inverse, then we get A transpose sigma inverse S here, and then we get A transpose sigma inverse times this part here. But that part here, according to the first equation, equals 0. So we come immediately to the conclusion that n times A transpose equals A transpose sigma inverse S, and S can be inverted with probability 1, and we assume that this will take place. So we will have that A transpose sigma inverse equals n A transpose S inverse. But then we see, we know A transpose sigma inverse, or have estimated it. And then we can insert that estimator here. And once we have inserted the estimator here, we come to a linear equation system. And it can be shown to be consistent also. So we have a solution here. And once we have a solution in B, we have also a solution for ABC. Then this ABC can be included here. So, and then we know, then we have a solution for sigma. So if you look at the solution here, it's given here, ABC is given this way, and I can express B, but it's not uniquely estimated because we haven't supposed any rank restrictions on A and C. And then S, you see, it's a sums of squares matrix given here. It's in fact Wishart distributed under normality. And then we have our dispersion estimator, which is given here. So what you can see, if you know a little bit about matrices, that these are projection operators. Here we project on a space with an inner product, and this is just the usual orthogonal projection. So this is the explicit solution for the growth curve model. And we can see that the distribution is pretty complicated. If you think about S as a Wishart matrix, we have the inverse here, and then we have something which remains on the mean. We can, however, calculate moments for these expressions here, and then we, for example, can use some Edgeworth approximation. Maybe more interesting is to compare this here with the MANOVA model. In the MANOVA model, the multivariate analysis of variance model, A equals identity. So here are the difference. So the only difference is that here in the growth curve model, we have included an A matrix. We have the same error matrix as before. But what I would like to sell a bit here now is some figures. This is in fact in some kind of tensor space for a growth curve model. This is for a MANOVA. And usually space here, it decomposes in two parts. One is a column space of the design matrix or its transpose, and one is also orthogonal complement. On this space here, the column space of C transpose, one estimates the mean by projecting the observations on the column space of C transpose. And on this part, we estimate the residuals. And from residuals, we can check models, and if we square residuals, we get an estimate of sigma. For the growth curve model, it's a bit more complicated because then we are in a subspace here, which is generated by the column of A. And we have an inner product here also because we have a covariance. The observations within a column are dependent. But in some way, we have the same picture. And what we want to do here is in some way project on this space here, but with an estimated inner product. So the estimation is in some ways two-step procedure, at least in the maximum likelihood estimator. So first we try to estimate the inner product or something so that you can find an inner product. And then we replace sigma by quantity. And in this case, we replace it with the sums of squares matrix. And the sums of squares matrix is obtained from these residuals. When squaring these residuals, you get the sums of squares matrix. Here was the definition, and here are the squared residuals. And then we have another space left also here for where there's some variation. But in the first step, we replace sigma by S, and this is indicated here. And once we have replaced sigma by S, we are in some kind of linear model theory. So then we just project here on this space. And this is what we could see on the estimators. And then we could add this R2 and 2 or R2 transpose to the S, and then we will get an estimator of sigma. And this was what turned out. Here we have the projections. Instead of a sigma, we have S here. Here's a projection of column space of C transpose. And here we have the sums of squares matrix. And here we have this extra space, R2 transpose. This looks like that. Okay, this theory or these ideas can be generalized when we have restrictions on the parameters. So here we have restrictions and bilinear restrictions. So B is unknown, F and G are known. And you can see it in the picture, this should correspond to this part. And when it corresponds to this part, we see that we leave the growth curve structure. So instead, we get the stair structure here. And this is what one can use. But I will not go into details anymore. So with the stair structure, one comes to what we call extended growth curve model or extended bilinear regression models. And there exist two versions of it. These are profiles. The model sometimes is called sum of profiles models. So these are M profiles we have. In the growth curve, we have only one. And the important thing here is that we have a nested subspace condition. Without that, we would not be able to get explicit estimators. And without that, we are in some kind of multivariate, seemingly unrelated regression model. And the other version is that we have nested subspace condition among the A matrices, like here. And in some way, these two models are equivalent. But since they're nonlinear estimators, it can sometimes be more advantage to use model 1 instead of model 2, or vice versa. And estimation about the extended growth curve model follows in principle the same scheme. So first of all, we will estimate the inner product. We do it with this part here, and then later we project in the first step on these spaces as a function of the parameters in this space. But where after projection we come to this part, we repeat the process. We update the inner product estimator with the space or variation in these spaces here, and then we project on this here and come to this part. And once here is a growth curve model, we know how the estimators look. And once we have found the estimators here, we update the estimators here as a function, say, of B3, and here we update the estimator, mean estimators given from here. And the sigma will be a sum of all these spaces or squared residuals from these spaces. Explicit formulas are given here. Here a Z matrix is an arbitrary matrix because I don't put any rank restrictions and I don't look at linear combination. I just look at the original parameters and they look like this here. They are not unique, but the covariance matrix is always unique. What you can see are these Q matrices, and the Q matrices were these projections on different spaces, which I mentioned before. And here are some explicit expression for these matrices here for the projection matrix. Identity P is a projection matrix, I minus P is also a projection matrix. And here you see the updated versions. You see that S3 is S2 plus something more, S2 is S1 plus something more, S1 is the sums of squares matrix here. Okay, and I will study now a special extended growth curve model, sometimes called G-MANOVA model. G-MANOVA means generalized multivariate analysis of variance model, and MANOVA is multivariate analysis of variance model. This was a generalized version, and you see it in the figure. The generalized version is given here. It's a growth curve structure, and here we have the MANOVA structure where we have the whole and space filled. We can also think about this as covariates for growth curves, or you have growth curves or some time-dependent covariates for the MANOVA case. Now we are going to put rank restrictions on this part here, and then you will see what happens. So here's a model I call G-MANOVA and reduced rank regression. Reduced rank regression because we have the parameter here and we will put rank restrictions on. We also have to put some kind of, for mathematical reason, that the column space of F transpose and is a subspace to the column space of C transpose here. And here are all matrices. I will not give the details, but we can see that the rank of psi should be less than the number of columns or the number of rows here. And this gives some kind of restrictions. This type of restrictions, it exists in the literature, pretty many examples. And I usually interpret it that if we have a lot of background information, which can be summarized with the help of some latent variables, the number of latent variables corresponds to the rank of psi. So for example, if you're interested in crop growth and we observed weather variables, for example, temperature, this you can observe every 5 minutes or even every second, but this is not essential. The resolution is too strong or too high. So, but the important thing is that there's some kind of latent variable connected to temperature, which will affect growth, together with some other latent variables also. But this has to do, so there the rank, for me, often depends, or I interpret it as a number of latent processes. The most important thing here, I would say, with reduced rank regression, if you handle it, is that you can, when you have a rank restriction on a matrix, you can always split it in two matrices or a product, like psi1 times psi2. If the rank of psi is R, then we have a psi1 matrix, which is equal to the rank of P times the rank of psi, and psi2, which is the rank of psi times the number of columns in psi. And these matrices can, of course, not be estimated, not be interpreted directly if you don't put any restrictions here. But we are not going to put restrictions. We are more interested in just this condition here, or the matrix here, to estimate it. And then we have this condition here, and I will soon explain why we need it. Here's something more, we can skip it, but we go to the model here now and look a bit how it looks like before we do some math. So here's the original model, the mean space here, and here we have residuals. And once we have residuals here, and it's not so clear what these are for, that it should be interpreted. We have just rank restrictions. And rank restrictions do not really, it just says something about dimension of the space. But it turns out that when we do maximum likelihood estimation, that we in fact determine that space also. So then it becomes also like a projection of observations, which is by far not the obvious that it should be, just because you say something about the size of a space. And here are the spaces given. Here are estimated values of psi1. I will give you some hint how to do it, but here also. So these spaces depend now on an estimated parameter. And this is a likelihood approach which gives it. And then the likelihood approach can then be interpreted. Also, that means that the residuals can be interpreted. So you can check the model pretty well under if you apply maximum likelihood theory. So here we have the model again, and then we have factor it, the psi1, psi2, and then we see and that this is a subspace, and if it's a subspace here, we are an extended growth model because we have a nested subspace condition. So what we can do, we fix psi1 first, and once we fix it, we have this nested we have an extended growth model, and then we know exactly how to estimate. So I will not give you details. I just show that in the likelihood we have a W, looks here is a function of psi1, psi2, B, and we have sigma inverse also, and now we're going to maximize it. And when we fix psi1, we know exactly how the likelihood will become, and it will look like this here, and W, and so sigma will equal W in the first step, and then we have to look at the determinant for W, which then only will be a function of 3 parameters, and B, psi1, psi2. And this we can handle also. And I will not show you the details. There are pretty many calculations, but when you know something about the extended growth model, there's not a big problem. I will just show you here in the end, one of the last steps in the calculation. It has to do with that we should minimize a determinant. In fact, we should minimize this determinant here because there are no parameters in S2 and R. So when minimizing elevation, what is K here? K is given here. It's a function of psi1. And we know from the previous treatment that we can get B as a function of psi1, and we can get psi2 as a function of psi1. So once we have estimated psi1, we have estimated all parameters. So this is a definition of K. And then we have matrices which are known. It's a factorization of a certain matrix. And yeah, so this is expression. And you can see that this is a semi-orthogonal matrix here, which is useful. And then we have the U matrix, which is also completely known. So we're going to minimize this expression. And of course, the minimum is just to do a singular value decomposition of U, or I'm referring to Poincaré separation theorem. Then we see that this is larger or equal to this relation, where the lambdas are eigenvalue, ordered eigenvalues of U. And equality holds when we have K as eigenvectors to U. So let's put the eigenvector, the Q2 eigenvectors, we call it the K tilde. And what we want to achieve is, and this follows from the definition of K, which was given here, that we want to find a psi1 so that this expression is fulfilled, so that we have the eigenvectors K tilde. Then we will get equality here, and we have found the lower bound of the likelihood, and that and then we are done, so to say. Then we have our estimators. So how shall we choose psi1 that we obtain a K tilde here? And this is in fact the easy. We just choose psi1 hat now estimated as a function here of the eigenvectors to K, and we pre and post multiply with this H matrix, which is a known quantity. So doing so, or I cannot show, it's just to insert, and then we will see that on both sides we will have K tilde. So this works. And then we can estimate the other parameters, and particularly we can see, and I will show you that the second term, the manual term here, is estimated through psi1 and the following way, and T1 and S2 also. And these come from the extended growth curve model. And here are some explicit estimates that are given here under certain conditions, so you can find out the expressions. And maybe not so most important is maybe the sigma here, that we can find an explicit estimate. The sigma means that we can start to test hypotheses and doing other things. So we had the reduced rank regression here. This is a G-MANOVA model. We had it with a reduced rank regression. You saw this picture before, and now we can define residuals because these spaces here are defined through this psi1 and the design matrices. And one can show that the residual space is a sum as expected, as it should be, as a sum of R1, R2, R3, R4. These residuals are given here. And by thinking about what happens, how these projections look like, we can start to interpret. If there's some data which deviates, say in R1, we can say that this for that data point, the model doesn't fit. And the same with other. And they have a different interpretation here a bit. But so R1 and R2 are in some way very much connected to individual observations, whereas R3 and R4 is more about the model, if the model fits to data. So I will finally just mention a bit about when you have restrictions on both B and sigma, because it's a bit interesting philosophic what is going on now. So we have the growth curve model now, and we put rank restriction on B, and we put rank restrictions on the covariance matrix or dispersion matrix of sigma. And it's unknown, but the rank here is known. It's not so that I can estimate it from data. So what we have here, we have our we have a growth curve model with some rank restrictions. It's maybe not the best picture, but we have here and some more restrictions which I couldn't illustrate, but it is that something, because if certain things are orthogonal to the dispersion, you will get some restrictions on data, or which should hold with probability 1. And so in some way, I guess the spaces which we talked about, they should act now inside some cylinder or some other space. And this gives some kind of general frame where inference can take place. You can see it a bit when looking at formulas a bit more. So here we made a decomposition of the whole space. We have the column space, the whole within individual space. We have the column space of sigma. We have something which is orthogonal to column space of sigma. And this is divided into two parts. And then we can see he has just shown how one can calculate gamma or the eigenvectors correspond to non-zero eigenvalues of sigma. But if you look at this, if you make a one-to-one transformation now, also sigma is or gamma here is unknown. So a gamma transpose y, we have the identity mass is something projected on orthogonal complement, and then we have something which is orthogonal to both A and sigma. If you spell out these relations here and see what models we have first that gamma transpose y equals this here, and then we have that since this part here is orthogonal to sigma, we get the relation of this form, and here we get something which is orthogonal, or y is orthogonal to both these things. Of course, one should be a bit careful because here equality means equality in distribution. Here it's in probability of a probability 1 because here's a mean, the variance of this relation is 0, and here is something also where the variance and mean is 0. So if you think about this equation, what we can see here now, one is that we put some kind of restrictions on the mean. If we have restrictions on the dispersion matrix, we also get restrictions on the mean. And this is important to remember because when we have restrictions on the mean, and if they're not irrelevant, they should be taken into account. Another thing is that we have data. If you replace, like in a likelihood, the random variables with data, data will probably not satisfy this relation. So then we should do some projection. But of course, we don't know the space of this space here because sigma is unknown. But it turns out that the column space here can be replaced, or sigma here can be replaced with S, which will give a space which is equal to this space with probability 1. But here are a number of open questions around how to handle it and if to take into account even this relation. But I think one really should do it. And then finally, how should we estimate the rank of the R here, or the rank of sigma? It's not, I don't know really how to do it. It's in principle component analysis, one usually has some ad hoc procedures. Of course, something can be done here also, but I don't think there exists any nice theory how this should be done. Okay, so this was my talk, so thank you very much. And before I stop at the very end, I would wish you all a Merry Christmas and happy and healthy New Year. Thank you very much.
Thank you, Professor Rosen, for such a wonderful and nice talk. For the interest of time, if the audience have any question, please email to Professor Rosen. Now we come to the very end of this session, and I have the honor to introduce another stalwart speaker, Professor Sujit Ghosh from the North Carolina State University. And Professor Ghosh is going to talk about possible hazards of proportional hazard models. So over to you, Professor Ghosh, and many of us fondly call him Sujitda. Over to you.
Thank you very much. And let me try to share my talk. I hope it is coming.
Not yet. Yes. Now it is visible. Yes.
All right. So you can see my screen, right?
Yes.
Okay. Thank you so much. I mean, thanks to Abhishek for inviting me to this conference, and I have very fond memories actually attending in person, and so that is so much of a fun. And also my regards to the memory of Professor Adhikari. I have fond memories of that, and I'll mention possibly one interesting conversation I had during the last meeting after this talk, so just wait for that. So this presentation is about possible hazards of proportional hazards. So it's an interesting, I think, a title, proportional hazards model that is heavily used in survival models. Is possibly the most cited paper in statistics, a whole of statistics, possibly over 35,000 or so in Google Scholars. Nonetheless, there are some issues when it is used as default, and I'll try to get to that aspect of it. So although I'm focusing on proportional hazards, but the similar problems that I'm going to mention also appears in other type of models, which is in the same realm of that is called proportional odds or accelerated failure time models. So these are very, very popular models routinely used in analysis, but they might have some problems, especially with some kind of treatments that are now being coming up, which becomes toxic after certain use and so on. So I'm going to highlight that. And so what are the possible remedies of that, and a little bit of theory circumventing that, and some open questions. So let's focus on a particular example, very simple example. We have two groups of patients in two treatment groups, one receiving the chemotherapy and another receiving the radio and chemotherapy. And suppose I want to compare their survival time. So, and this is particularly in terms of gastric carcinoma, and they are randomized into two groups with roughly equal number of patients. But as it is common with any survival analysis, the survival times are not always observed because the study sometimes is ended because of the lack of funding or time aspect of it. So some observations get censored in the sense that we don't know how long a patient would survive, because the moment the study is stopped and data collection stopped, there are patients which survived, which is a good thing, but we don't know survived on either of the treatment groups. So censoring can happen like that. So to save some notations, suppose I denote the survival function of the group 0 as this. That means the probability that someone will survive beyond some little t amounts of time. This could be in days or proportion of years or something like that. So there's some unit of time. And S1t is another survival function for the second group, which I call z equals to 1. So there are just two groups who are going to generalize this. Now we are comparing two functions here. So the question is that how do I actually compare two functions? We have to come with certain type of discrepancy. So one is I take the simple difference and then I integrate now. It's still called integrated one, which is going to lead to kind of difference in the mean. But it is not possibly a good idea to have the same kind of weight throughout the time period, because as you age, it is more likely someone is going to die. All of us are going to die at some point. So there will be possibly need of weight function. And nonetheless, it will depend on the choice of the distance. But what I'm going to talk about is how to even estimate the whole function. And then you pick your main discrepancy, distance or some kind of a discrepancy and measure that way. To set notations, because of censoring, the survival time is t and the censoring time is c. That means that suppose a study ended at, say, 8th year, and we only get to observe the minimum of those two. So if someone actually died, then we know what is the survival time. But if they survived, then actually we don't know. We know only the censoring time. So this is called right censoring, and we all know about that. So typically you observe this triplet and we assume that these are IID. So here we are not assuming that here we are assuming T and C are independent conditionally on the covariate, but the whole triplet are IID from some joint distributions. And we are not making a particular assumption yet what kind of joint distribution. But let's think about some of these scenarios that can, these are hypothetical, but I'll come to more realistic ones. So if there are two groups and I observe the survival functions to be this solid blue line and the dashed line, and clearly if this is the group 1, then clearly group 1 survival rate is much higher, and we will declare the patients which were in this group, group 1, have survived no matter what time point. So here, if I choose, say, 200 days, clearly the probability of surviving beyond 200 days is about something like 25%. But if someone is on this treatment group, it is close to something like 75%. So it's much, and that is true no matter what time point I choose. But this did not be the case in certain other situations, and this can happen. So in this case, if I ask which one is doing, which group is doing well, if I would have chosen a time point somewhere here, of course, group 1 seems to be doing well by the same criteria. But if I choose time point at, say, 200 days, then the thing have switched in between at, say, something like 100 days or so. So in this case, can I answer the question, which group is doing well? Well, it's tricky. And this is the type of situation that motivates the whole talk. So as long as you get this idea, what is the problem? This is the problem. And why this can happen these days? I mean, we are getting more and more sophisticated drugs, but at the same time, they have toxic effects. If you look at any advertisement by any pharmaceutical industry of a drug, I think they spend 75% of the time saying what are the side effects, then what is the benefits. So what happens is that you tend to survive in the beginning quite well. I mean, it has a better survival rate, but then it becomes so toxic that people start to die, and that's why this crossing can happen. So that's one possible explanation, but there might be different things as well. More theoretically speaking, how do we handle this type of situation if we were to compare two groups only? And things can be tricky. In this case, for example, one would possibly say that, well, group 1 is pretty much good, and there is still a crossing, but because the crossing actually happened after something like 500 days, and both several crops has probability less than 20%, so maybe this crossing has not much effect. Although when you are talking about human life, I mean, any survival is good. So any gain, even in this period, is a better thing. But here, that toxicity possibly happened after a much longer time. So maybe you would decide that it would be, see, if I'm asking you what group you would be or your loved one who you would like to put on, it is a tricky question. So how do we handle this situation, and what's sometimes wrong with the current models? And they are particularly related to this aspect of it. So I'm now going to expand on this. So what is proportional hazard? In this particular simple case of just two groups, if I can get the hazard function. So hazard functions, several functions are interchangeable in the sense that one can obtain from the other under certain very mild regularity condition. So hazard function has this type of definition, and proportional hazard exactly means that the ratio to hazard function is constant, which was a breakthrough in 1972. David Cox proposed this, and since then it has been used heavily. As I said, it is one of the most cited papers in whole statistics. Because it has been a breakthrough in that sense. And since then, there are many other things. Accelerated failure time is defined like that. Proportional odds is like that. But there is one interesting aspect I think might have been overlooked, but now I think it's well known, is that none of these models will allow for the crossing of several functions. For example, this model, or if I have some functions like this, none of this can be captured by any one of these models. So it is not a matter of choosing a particular hazard function. No matter what baseline hazard function you choose, none of this. The reason is very simple, actually. If I look at this thing, hazard function, I mean, the proportional hazard can also be expressed equivalently in terms of several function, which is like this. And eta is the same eta here. So now there are only two possibilities. This eta is positive, and this is a legitimate one. Both are several functions. For that, eta needs to be positive. So there are only two possibilities. Either eta is bigger than 1, less than, or equal to 1. If it is equal to 1, two several functions are equal, so there is nothing to compare. But if eta is bigger than 1, then the several function of the first group is always less than that. So in that case, always the group 0 would be better than the group 1. And if eta is less than 1, it is the other case. But the important thing is that this is for all t. So which tells you that there will be no possibility of crossing several functions. So if I use proportional hazard models, then I cannot capture that type of crossing several functions. And there are other situations where this cannot be captured, for example, delayed separation of the several function and so on. But not only this proportional hazard, the same thing, that the thing that is in this box is true no matter what model you choose to do. And this is completely semi-parametric models. It doesn't matter what you can choose, gamma function distribution, inverse Gaussian that Dr. Chove was talking about. No matter what hazard function or several function you choose for the baseline, this is the same problem that is going to happen. So this is exactly the problem. Okay, hope that's clear. So now let's talk about a real life situation, the same data set that I began with. Now this is the plot of that. And in the two sample case, it's relatively easy. I can get non-parametric estimate, which is the Kaplan-Meier estimate, another possibly most celebrated paper in statistics. And it was a breakthrough as well, which provided the non-parametric MLE of the several function. And if I use that, then it clearly actually captures this crossing in this case. And here the crossing happens around about 1000 days and so on. But suppose I didn't observe that. I blindly, now there is machine learning, we blindly fit models without thinking about sometimes what is the consequence. So suppose I fitted proportional hazard models to the same data sets. This would be the estimate. So here it will say that, well, the people in group 0 has a complete domination because it never allows for the crossing. So one has to dominate the other, or they will be declared the same. Here possibly they will say there is no difference, but we see that there is significant difference here and so on. So that would be a consequence of making wrong assumption about a model, given that it is still semi-parametric, it is still a wrong model in this case. So I put this kind of biohazard sign here. So all of these pH, AFT, and PO, they are dependent on their own assumptions, and we need to possibly verify that. And there have been tests to do that, but let me go through some other situations with simulated data. So I'm going to simulate data from, say, log normal distributions and the censoring time from exponential, and I choose some parameters. So the second case is actually favorable to AFT, and the first one. So I'm going to possibly show you the graphs, which is easier to see than actually looking at these numbers. So I'm going to show the estimates obtained by Kaplan-Meier and also assuming proportional hazard, and what are the consequences of making such assumptions. So let's look at the first example. So this is the ground truth. That means here we know, if I know that true several functions, we see that there is a difference of survivals at, say, at this time of the year, of the days here. But if I fit a Cox models to this data set, then the estimates will show there is no difference. Of course, there is a significant difference here. The reason it happened is that most of the time it was bigger than that, so it kind of said no difference. So this difference that happened here was completely missed. So the pH assumption leads to no difference between the two several functions, although there is a significant one. And if I fit Kaplan-Meier, it clearly estimates that very well. So that's not a problem. And in this case, if there is a test for proportional hazard, it will be rejected. So you'll be possibly safe if you're doing this carefully. But if I'm not doing that here, I'll wrongly conclude there is no difference between these two treatments when there is a significant difference. So that's a consequence of making wrong model assumptions, even at a semi-parametric level. Let's look at the second situation. This is actually generated from an AFT model, but suppose I fit pH. So in this case, look at the difference in the two several rates at this, say, at 200 days. There is this difference. But now suppose I fit Cox proportional hazard. So here it correctly identifies group 0 is superior to group 1 is superior to group 0, but it actually inflates the difference. So that's another problem. So here there is a complete dominance of one group and other of the other. In this case, group 1 dominates group 0. That means they have better survival rates than the group 0. But if I look at a difference in the survival rates at a particular day, say in this case 200 days, it will report inflated difference. That means it will possibly show more benefit of one treatment than the another one at a particular day than it should be. So that's another. So you can see that in this previous case, there was a difference and it annihilates the difference because of the wrong assumption. In this case, there is a difference. It correctly detects the difference, but it inflates the difference. And more troubling is that if I do a proportional hazard test, in this case, sometimes it will not even reject it. It will think that, well, maybe this is because it's a statistical test. It possibly doesn't have that much power with the limited sample size and censoring going on. But if I would have done Kaplan-Meier, it, I think, correctly estimates that. But the problem is that with Kaplan-Meier, I cannot do, I mean, if I have more covariates and so on, if I just have more than two groups and so on, or I have continuous covariate like age or something, I cannot use Kaplan-Meier type estimator. So I hope that tells you what is the problem. So let's generalize this to vector valued covariate. And so no longer the Kaplan-Meier it can be used. And our goal actually is to use this conditional survival function. And if I can estimate the survival function, we can also estimate the hazard functions because they have one-to-one relation under very mild conditions and so on. So our goal is to do this or do that. I can either estimate the hazard function directly or the survival function, and I can get one from the other just by transformation. So now the generalization to a vector valued covariate is, this is the original formulation, and for accelerated failure time is like that and proportional like that. But as I said, more generally, actually all these three models falls into another more general model called time transformation model. So it is the transformation of the time is regressed on some regression function, and the transformation itself can be estimated. By choosing certain error or transformation, all of these models can be seen as a special case of this time transformation model. So this is a more general model than all three cases combined. But even for this more general model of time transformation, one can show by the same argument that I've given for proportional hazard few slides back, that it will not allow for crossing of several curves. So one has to completely dominate the others. And that's the problem with this type of, these are very general, semi-parametric, almost non-parametric models, very flexible, but nonetheless, it has these inherent problems. And that has been observed more recently because now we are using more sophisticated drugs and they have toxic effects. And so we need to know when to stop a drug unless, we use this type of models which will not be able to detect such things. So this is a practical and a theoretical problem. I hope you find it interesting. So, but what are the remedies that have been done? Typically, what one does is that make the coefficient of this. So this is the proportional hazard model. I think a couple of sides black. So here, this beta coefficient is made a function of time, and so that it is not going to be a proportional hazard any longer. But my point is that once this nice structure of proportional hazard is gone, and the beauty of that theory is that you don't have to specify the baseline hazard, and you can still estimate the coefficient beta using what is called partial likelihood theory and so on. It has beautiful asymptotics and so on. But the moment you lose that, why insist on that particular structure at all? Because then we don't have the proportional structure. And of course, one can alleviate the problem of proportional by a time-varying a beta coefficient, but also it will not have the same interpretation as before that it used to have. So once the separation of the time and the coefficient is gone, I think there is no point in insisting on keeping this particular structure, because the whole beauty of proportional hazard assumption that alleviates the estimation of baseline hazard is no longer possible. And you can make piecewise exponential kind of models to model the baseline and so on. So, but if you're going to do that, why insist on that? So there might be other ways. So there have been other attempts called hazard regression, which models the hazard using some kind of a linear splines, and that actually can alleviate some of these problems, and it is more general than that. But let's look at what is the impact if someone is sometimes doing machine learning type models like variable selection and so on. So we recently investigated that with a student, Alvin Streng, and we published that in a paper. And I'll just try to highlight the problems and then the remedy later on. So this type of time transformation models, which covers all of these things, were explored also by one of my postdoc previously. And at that time, we didn't address this particular problem of crossing edges, but nonetheless, it provides estimation theory of this. So let me highlight the problem. So here, this was a simulated data experiments, which is similar to a very particular ACTG HIV data. So here the true model is pH. And if I'm trying to do variable selection, if I use a penalized proportional hazard models, which are now available in our software, so you can fit these things very easily. It looks like the penalized ones actually have a problem, although the regular pH model works quite nicely in this case, and this other non-parametric models also works quite well, but the penalized model somehow actually does. So here I'm trying to see how many times this particular covariate, which has a significant effect, will be picked up by a variable selection methods in a simulated data scenario. So it says that, well, if it is active, it was picked up 99%, which is good, but the penalized method only picked, so this was a lasso penalized method and elastic net based method as well. And they are biased, we know, and that possibly leads to this type of problem. But if the true model was AFT, I mean, both of these things are going to suffer from that. That means here this particular covariate was inactive, but it was picked up 44% of the times. But with the penalization, because it penalizes against having too many covariates, this actually fixed this problem. But in this case, that problem is not fixed. But the other method, the HARE and other things, which I'm not speaking at the interest of time, they actually correct those things. So my point is that when you are fitting these things, you need to be aware of the assumptions you're making and maybe check that. And the less assumptions you can make, it would be, of course, better, but it becomes difficult analyzing theoretically. So now let me come to the type of models that I have worked on in recent years. And so for the time being, suppose there is no covariate and I want to estimate the hazard function. I will bring in covariate in a few moments. Suppose this is the hazard function I'm trying to estimate, and I represent the hazard function by some kind of a basis expansion. And I mean, that is typically almost any function in a Hilbert space theory, we can do that. And I'm doing a finite one, but this M will be let go to infinity with the sample size and so on. And then the interesting thing is that if I take a basis function approach to represent the hazard, so these are some basis function that I'll choose later on. So it's linear in the gamma. So gamma is the parameter, but the dimension of the gamma can be varying with the sample size. That makes it non-parametric here. So the cumulative hazard function can be also written like that, and this would be the integrated function of basis functions. And the fact that these are both linear in gamma actually makes this problem theoretically much more convenient. So what we used is called Bernstein basis functions. And if you are aware of that, you know that this is a class of basis functions which preserves the shape of a function very well, if you know that, because in this type of literature, reliability theory or observable analysis, having increasing hazard, decreasing hazard are important if you actually want to carry that. We are not going to do that, but here those things can also be done, and that's the purpose of that. And it has nice convergence properties. It has the supreme convergence on any compact sets. So that makes it is interesting, and we have to do little tweaking at the end so that it is a legitimate hazard function. Because any non-negative function is not a hazard function unless its integral is infinity, because the Savell function to infinity is 0, and so that can be maintained as well. So if I write down the likelihood function, interesting, the likelihood function can be written down in this closed form. So we are not making any assumption whatsoever about the underlying hazard function, except for the fact that's a continuous function, that's all. And the hazard function has this form. It is non-linear in gamma, but the interesting thing is that we can show that this function is actually, this is a concave function, and it's strictly concave function. And so it is as a unique maximum here. And we can find that numerically as well. So that's the thing is that this particular form that we can get, what we can show is that even if you bring the covariates into your model, we will get the same form. So that's very interesting in general. So even with the regression models, we will have the same from the likelihood. So it will enjoy the same type of theoretical properties that it will do without that. And in order to show that, if there are just kind of 0 and 1, the two groups, one that is easy to show, and one can show that with the expanded coefficients, it can be written like this. But even if you have continuous or mix of continuous categorical, the dimension of these gamma coefficients are going to increase a whole lot, but it can nonetheless be written in the same format. And some of these things were explored a few years ago, and we have some theoretical properties of that. Not only that, the Fisher information actually has a closed form in this particular case. Here I'm writing the Hessian, so negative of that will give you the Fisher information. And one can show that under very mild conditions, this is a positive definite matrix. So that also shows why it has a unique maximum. So now talking about the theoretical properties, because we are talking about function as a parameter, so the parameters are not really real vector, it is a function. So we have to come up with some kind of a functional distance. So I'm using what is called the Hellinger metric between two densities, and these densities are being obtained by the hazard function. So if you specify a hazard function, you can get a density functions, and this pH at the induced density function given the hazard function. And the distance between the two hazard is intrinsically measured by the distance in the Hellinger function that this hazard function induces on the probability distributions. The reason of choosing that, this is a good metric. It is bounded and so on, so it allows you to do some theoretical investigations. So, of course, none of the theory can be done without certain assumptions. So if we make certain continuity type or smoothness assumptions about the hazard function, you can show that the methodology that I just described is going to give you a consistent estimation. To get consistency, actually, you just need that number of degrees to go to infinity at any rate. But if I want to get a rate of convergence, that means how fast it is converging, so in terms of the Hellinger distance, this would be the rate that is going to be based on the regularity condition. So in that case, that m has to increase with the n with certain power, and that power is given by this. And of course, here I don't know, this is not adaptive yet. That means this rate is dependent on the Holder constant or a continuity constant power that we were using here. So, but nonetheless, it tells you that it gives you the convergence and also the rate of convergence. So having obtained that, let me come to how does actually it performs in some of the examples that I was talking about before, where the typical AFT, PO, proportional odds, pH, proportional hazards cannot handle situations. So in this case, in order to measure the accuracy of the estimates, I am taking some kind of a L1 distance between the true several function and the estimated one up to certain time point t, because things are censored. So this tau is chosen such that the probability of several is less than 0.01%. So that means no one cares about that. If someone has a chance of 0.01%, there is no point looking at time point beyond that. And that allows us to do the theoretical investigations at the same time. So with the same type of data sets that I have shown from log normal. This is the same data sets that I was showing to motivate the whole thing. In this case, if I apply this type of Bernstein polynomial-based estimation, it achieves the accuracy very well compared to the Kaplan-Meier. Even it improves on the Kaplan-Meier, both are non-parametric in a sense, and also HARE, that's the competitive method that also existed. And if I look at the percent of the time, the BP actually has the smaller, out of all 1,000 simulations, 60% of the time it will have the smaller one. So it achieves the accuracy much often than the other two non-parametric methods. But what about going into kind of regression models? So now suppose the data actually is generated from an AFT type model, so also a special case of time transformation model. And I take the mean function here to be a kind of a complicated one. It's not linear in Z any longer, but it still has the AFT structure. And here also the error distribution might depend on the covariate itself. So it's a more complicated models than typically entertained. But in this case, how the BP performs, because here we are not making any assumptions about the underlying models. So in this case, again, it achieves under 0% censoring, 30% censoring, and 50%. This is the most tough one. It achieves the best accuracy, and it wins over the other methods most of the time. What is surprising, you will find here, even though it is an AFT structure, but if you assume a linear form of the mean function here, AFT actually never achieves that. So even having a right structure, but a wrong specification of the mean function itself here, which is a typical one. Typically, we take a linear function, but if it was not linear, it will achieve 0% winning against any of these methods, although it has the same structure. So that kind of cautions against, basically what I'm trying to say, it cautions against a lot of structural and distributional assumptions that we are making while doing this type of models. And this is particularly important because we are talking about sometimes human life, its treatments, miscalculations like that can have a disastrous consequence. And I'll also try to give you, and in this case, the BP actually performs very well compared to the other methods. Yes, I think I should be able to finish in 5 minutes or so. Thanks, Indraland. So that's the caution. So let me end with a particular example, and this is one of the most famous data sets, and sometimes it is overlooked, some interactions, because people have assumed typically some kind of proportional hazard or accelerated failure times type models, and they missed something that I'm going to point out. So typically, there are, say, let's say 2 treatment groups, but there are 5 covariates in the baselines. And one of the most prominent one is called Karnofsky score. 0 means that person is almost dead. 100 means that someone's health status. So it is a index-based scores. The higher, the better in this case. And because we are looking at lung cancer is actually known to be associated with particular cell types, the squamous cells, the small cells, and adenocarcinoma and large cell. And they have a very complicated interactions with the treatment. I think this is one point that has been missed by many other studies previously, because they never cared to look for more complicated models, and I'm going to tell you that. So this is, as I said, lung cancer, and adenocarcinoma happens in this part of the lung, the squamous cell happens there, and the large cell typically happens there. So the cell types are hugely important, and if you talk to a doctor, they will know this is the case. But what is the connection between this type of cells and the treatment? I think that's very less understood so far. Let's try to explore. So now if I take the BP-based model and fit that, and I get the conditional survival function. So here we are looking at a combination of treatment is 1 and treatment 2. So 1 is standard chemo and there is a experimental chemo. And then there are 4 cell types. So if we look at that, and suppose I look at what is the chance of survival beyond 200 days. And you can see with the Karnofsky score, it has a kind of a non-linear interactions here. But what is interesting is that suppose they are in the same treatment groups, they both are in the experimental treatment group in this case. But suppose they have two different cell types, cells type 1 and 2. And remember, I defined the cell types before, which is the squamous cell and the small cell. And there is a drastic difference. So even if they are getting the same treatment, the survival rates is much, much higher compared. Here, there is no survival, almost zero chance of survival. If this treatment is given to this type of people having this type of cell, affected cells, then there is 0% and with the same treatment, but with the different treatment and the standard treatment actually has a better survival rate in this case. But these things were not different if it was on the first type of cell. So you can see there is a very complex things going on, and this might be completely missed if we would have done more simplified models like AFT and things like that are typically used. And if I look at the two other cell types, again, you can see the drastic things that are changing. So there is a very complicated interactions between the treatment and the cell types for the lung cancer, which possibly have been missed, and it might have a disastrous consequence. So this is not only a theoretical problem, there is a real human impact of assigning treatments and not knowing the interactions of the treatment with the cell types can have a disastrous consequence. Anyway, so I would like to finish my talk with some of the things that we have presented, and it is both in theory and in practice an important problem, and we should not keep we should keep track of the assumptions being made, not just for theoretical reasons, but for the consequences. But there are also some problems that are still open. For example, here I gave the asymptotic rate, but here I have to know some continuities. It is not adaptive to the smoothness conditions. There might be a good idea to do that. And in this case, the type of models that I described are possibly good for only few covariates. But if I have a large number of covariates, a penalized version of this type of models that I presented might be useful, which is still under investigations or development. But one thing I should note, there has been some very interesting development. Although we tend to use this type of lasso, adaptive lasso, elastic net, and things like that. But if I put some kind of a shape restriction, you don't actually have to put any penalization. The shape restriction itself acts as a penalization. And there are some kind of nice results, like if you put some kind of sign constant and so on, it achieves the oracle properties without penalizing anything. And there have been some kind of concentration inequalities and so on. So there is some interesting theory one can actually work out in this type of problems, because here we know we are modeling several functions. There is a shape restriction. It needs to be decreasing functions and things like that. So we might be able to develop methodologies without putting some kind of a construct. Like lasso is a good penalty, but it has no possibly inbuilt assumption that is useful for survival analysis. Anyway, I think these are some points that I wanted to mention. And if you allow me, I'll entertain questions if you have any. But let me end with a little story and fond memory of Professor Adhikari. Last time I attended, I don't know whether some of you remember, I have an incident. There were some books on the display, possibly from Springer. And I think one of the book was lost or something. And I was just talking to him and said, that sounds unfortunate and so on. I think I still remember he saying that, well, that's not possibly a big deal. I think he said that in Bengali, but I'll try to paraphrase in English. Is that, well, if someone has taken mistakenly or someone just took that, at least that has increased someone's knowledge. So even if the book is lost, it is actually increased someone's knowledge. And that was the type of person I know about him, and I dearly miss him. And with that note, I'll end my talk, and happy holidays, but have a safe one. Thank you very much.
Thank you, Professor Ghosh, for such an interesting and extensive talk and sharing with us nice memory of departed soul, Professor Adhikari. And I just hope that it's quite an interesting that you have mentioned several open problems. And I hope that researchers and practitioners working in this area, including yourself, will be able to find solution to the open problems that you have presented. It's very nice. So if there are any questions from the audience to any of our speakers for this session, anyone? Okay, Professor Chobe, you have question.
I have a query for Sujit. I was kind of curious when you're talking about Bernstein polynomials. Don't you need the support to be 0 to 1?
Well, but I mean 0 to 1. I mean actually any compact support can be transformed to 0 to 1.
Okay, so that's what my question. Are you transforming to and then using the Bernstein functions?
Yeah, so as I don't know, maybe I can bring up, or there was something called a tau, so that I choose several times, say a largest time tau, such that the serval function falls below certain epsilon. Like in practical terms, suppose someone's chance of surviving is below 0.1%. So I choose that tau, and that tau is a fixed number, even if it can be infinity, but there is a positive tau for which the serval function will fall below, say, 0.1%. And I'm choosing that tau. And in real application, I'm taking that tau to be the maximum serval time, censored or not, to estimate such a thing. And one can show that will almost surely converge to the support of the distribution. So that's how I'm handling that aspect. And I know you are not very expert on Bernstein. We heavily use some of your results that you have published.
No, we do mention that you can use it after transformations in many situations. However, I just wondering whether like Poisson weights, like we have used in our statistics and decision paper, you are aware of that?
Yes.
For survival function estimation, where that could be used directly without any transformation.
Yeah, it involves the infinite sum though, but yeah.
Well, in practice, you don't need the infinite sum because at the maximum survival point, the survival function is 0. So after that, the weights drop out basically. And
I think that's exactly what we did. That how I was talking about is exactly that the maximum survival time.
Yeah.
And so I think, and in practice, I mean, because it's a linear transform, it doesn't affect the estimation properties as I tried to show through simulations. But yes, I think that's another approach. I think that approach I used for another talk, which was presented in this conference, to estimate the mean residual time, and we used your Poisson trick for that type of estimation problem.
With that comment, let me also say that I enjoyed your talk very much. Thank you.
Thank you. Thanks. That means a lot to me. Thank you.
I think you presented something like in the conference in July, but I was not able to attend your talk.
Yes, I think, yeah, I was hoping this was, hopefully this is not a total repeat for you, but
no. So that's why I enjoyed it. Yeah, thank you.
Thank you, both of you. Are there any other questions for our speakers?
And thank you, Dr. Sinha, for your nice remark on the chat.
I think Murari Singh has raised his hand, looks like.
Very nice presentation, good talk, good work. Maybe I might have missed actually this point. Did you try to estimate the point of cross-section where the two curves are crossing?
I did that. In fact, in our method, we are able to estimate that point of crossing as well. Yes.
Okay, that's good.
Great. Any questions? Any from the audience? If not, let me thank all the speakers for such a wonderful talk. And over to Professor Dr. Abhishek Odhikari.
Thank you, Indranil. It's my great pleasure to say thanks to all of you, all the speakers, along with the chair of this session. It was really nice interactive session, and that's the end of the technical session of this conference. So it's time for us to go directly to the valedictory session. So as usual, every end of this technical session should have this valedictory session. So without any kind of delay, I just directly go to the audience. But before going to that, I think Lena is with us. Lena, are you here? Lena, Dr. Lena Trell?
Yes.
Okay, so we actually celebrated your birthday without your presence, maybe. I just at that time, but again, wish you a very, very happy birthday. So every year, I just shared few slides before the session started. Just for your sake, I just again repeating the slides. It might be a repetition for all, but maybe a good memory for all of us. Just a moment. I just share a bit. Yes. So can you see this? It's 2017. Can you see my screen?
Yes.
Yeah, both Eric and Professor Sengupta and others are all there. And we had a cake cutting ceremony. So every year we celebrate this day, this 23rd of December every year. So this year, a special year for Lena. She will be 80 years old now. So very many happy returns of the day. And wish you all the very good health and all. And so usually when we have the conference in a physical mode, so there we can see many faces, known faces. So it's like our family. So we miss all of you, though this year or last year we had virtually, but still. So here we are having, not having Professor Saha and Professor Adhikari with us, but I'm sure that their blessings are always with us. And with that, may I now request you to say a few words. Maybe we can start with Lena on your birthday. Lena?
Thank you.
Yes.
Yes. Thank you very much for this great celebration on my 80th birthday. You know, looking back over the years, the kindness, the feelings and warm wishes I've had from you are the dearest of my memories and have given me inspiration, knowledge and strength. Central in this has been and remains the great and most beloved Professor Mahim Anakari, who introduced me and Eric to India and Kolkata and to his wonderful family and relatives. Always kind, friendly and helpful, he showed and taught us so much about India and Calcutta, taking us on excursions around this city and together with his fantastic family who took me to explore the cultural life of Calcutta and even to Turkey. All of this comes together now and makes the 80-year celebration to my warmest memories, both on the personal level and scientifically, engaging me as chairman and so involving me in the conference. Ed Abhishek has continued in the great spirit and standard of his father and arranged and led as a world-class virtual meeting for today and the future. And I already long to come back to the next meeting.
Thank you, Lena, for your nice experience with us. And it was really great pleasure always for us to interact with you in person. So we are really glad to you as a family member. Thank you. Yeah, I'll request Eric to share a few of your experience maybe regarding this conference and all.
Oh yeah, what can I feel but enthusiasm and happiness? I mean, it has been a so exciting conference, so really perfect, so that one is full of inspiration really, and it has been impressive, the kind of sharpness and mastering of the time. Not me, of course, but everybody else has held times and managed the computers and everything so perfectly that you really can't feel anything else than gratefulness and joy. And just as an example of the impulses one has had is the enormous topic, the kind of disposition of this meeting. I mean, I read here everything about, well, sharing, secret sharing, very openly shared, by the way, and disaster management and computer model to interpret Gaussian process model and convergence in topological spaces and perfect numbers and illicit drug addict and Lorentzian wormholes, fascinating things, and rough set theories in the study of COVID-19. So COVID-19 is brought very remarkably in this conference. I mean, it's at least 3 of the topics here deal with COVID-19. We go on with, for instance, awareness program on diabetes mellitus. So we have medicine, and we have flat plane solar collectors, and we have mathematical anxiety and performance in schools where COVID-19 is on. And we have relation to stress and mathematical performance. This is a very nice medical research object now, relation between stress and almost everything. And now we live in a stressful environment. And we have a fascinating space of positive measures. That is the ideal space, I would say. I would like to be in the space of positive measures. Think positive, be positive. And we have liquid crystal flow, and we have color, the deepest color and music theory. To bring color and music together, this is a feat. And we have tumor immune interaction model. And we have carbon dioxide emission in Gujarat and Maharashtra. And we have nanofluid flow. And we have F-learning tools during COVID-19. We have scenario in investment behavior. We have service for boilers, and we have product life cycles, and we have control strategies for tumor cells, and we have phantom scenario, and we have manifold co-primes, and we have hazards of hazard, and even lung cancer. So you couldn't really think of a richer and broader program than this, in my opinion. So this is, you could say, honor mark of IMBIC. And everything brought forth by enthusiasm and young minds, innovative, ingenious, and bringing hope for the future, in my opinion. And over all this, so to say, streams the karma and the nice spirit of Professor Mahim Adhikari. And you, Abhishek, has conveyed this so talentfully and also strict and controlled to the futures to come. And I wish to thank you for a fantastic meeting this year. Thank you.
Thank you, Eric. May I now request Professor Chove to say a few words?
Thank you, Abhishek. It has been a tremendous, satisfying meeting, actually. And it has gone very smoothly. I couldn't join yesterday, but I heard the summary of Eric and very aptly summarized the whole meeting. And I'm so glad how smoothly it has gone. I want to share my one of my pictures when one of the pictures of Professor Adhikari, not my pictures. I'm with him, actually. So I want to share that. And then I want to say another couple of words. Let me see. So that's 2016. I thought it was, I was there in 2019 also. I think the picture which Abhishek you shared, they're somewhere hiding, I guess. So this is the kind of memory I share of Professor Adhikari, and it always looked same. I mean, it was such a shock again. I was just uh, not repeating the same thing again. But we'll cherish that memory forever and ever. So with that comment, I I congratulate you for having such a wonderful gathering and meeting and quality of papers. I mean, you yourself, it was mentioned somewhere, you and your family became sick of COVID, and without with that kind of pulling this kind of meeting is commendable. I mean, I'm actually I have experience with that. I held a meeting in July. I think Sujit that was there. So it's wonderful. Now, last thing I want to say is I really commend and congratulate Avi Priyo. I was so impressed by the time, by the method of delivery, the annotations, and for such a young kid, I mean, looks like a pro. So with that, I congratulate you also. I mean, to train him to that feat, and congratulate to all your family, and happy holidays and happy New Year.
Thank you. And it must be very enthusiasm or enthusiastic. My son, he will be very happy to hear this. I'm sure he is not here, but I will surely convey this message to him. Yeah, may I now request Professor Manikam to share a few words. You are muted. Yes.
Yeah. Can you hear me now?
Yes.
Okay, good. I think the conference went really, really well. I would like to congratulate Abhishek for arranging such a nice conference. He did a really good job. And the talks were really of high quality. Particularly, I can say about graph theory papers, they were really good. I enjoyed the talks. And some of the work they have done is remarkable, actually, really good papers. So I want to congratulate the speakers on that. And I'm looking forward to the conference next year. Actually, it's wonderful, wonderful. So I wish you all a very safe and enjoyable Christmas holidays and a happy New Year.
Thank you. Okay. Sujita, would you like to share anything more?
Well, I mean, as I said, I have very fond memories of Professor Adhikari, and I remember having good time visiting you all in the conference. And although I was not able to attend yesterday, I really thoroughly enjoyed the virtual conference as well. But I must say that the in-person is so much of a different experience, and I look forward to having that maybe next year, and hopefully it will be in person. With that note, happy holidays and have a safe one. Thank you.
Nonil, would you like to say something?
Well, first of all, thanks to you and all other organizing members of this wonderful conference. I have learned a lot in watching these virtual presentations, and also I want to thank you for giving me an opportunity to chair this session with a lot of these speakers from whom I have learned a lot through their papers and articles. It was very nice experience for me. I also have some very sweet memories back in first time I attended in person back in 2012. And I don't have any trouble to say that during winter time in Kolkata, and especially I enjoyed thoroughly the food as well with the conference. So it was very nice, and I hope that we will soon be able to, from next year onwards, to meet in person and have nice chatting in person. And I want to offer my best holiday wishes to all of you for a happy Christmas and the new year 2022 ahead.
Thank you. May I now request Professor Shengupta, Professor Ashish Shengupta. It would be nice to if you all switch on your camera, then it would be easier for me to find you out.
Okay, can you hear me?
Yes.
Hi, Abhishek. Yeah. So, well, what more can I add? It has been a fantastic conference. You are carrying the flag very aptly, very professionally. In a conference, we look forward to the papers, quality of the papers, also to the organization, and finally the environment. Well, the last one is, of course, physically it's not there, but definitely even through our virtual conference, we did meet people. We are able to chat in between, share some of our thoughts. Then, obviously, the papers have been remarkable. Some of the papers definitely. In statistics, we got very nice papers. I enjoyed, I learned also from various disciplines. It's a multidisciplinary conference. And finally, organization. What more can be said? Given all the constraints that you had faced and you had come through, both physical, emotional, as I mentioned, it's a superb job. Okay, and obviously, Ovipriyo is one of the upcoming persons. We'd like to see him in the next conference again. Okay, it was a very delightful thing to see him at this conference, the way he performed, and definitely, hearty congrats for a very gala, successful conference. Abhishek, have a very happy New Year to all of you, and have a very pleasant and safe one too. Thank you.
Thank you. May I now request Professor Murari Singh to share a few words?
Well, thank you very much, Abhishek. It was actually a new conference to me when Professor Chobe informed me that he would like to present this paper and this work. That's fantastic. I said, I cannot register if there is money here. He said, no, there is no money involved. So actually, I joined this morning session only, beginning with the artificial intelligence to the last one, was crossing over of survival curves. Actually, very useful topics were presented, professionally handled. And I really enjoyed whatever talks I attended this morning. And I can only say that it has been so well organized, actually. So my congratulations to you, Abhishek, and your team, actually. It has the job well done, actually. And a lot of, based on this, I can also estimate that most of the papers presented in the past must have been of the very high quality. So congratulations again. And good to see many of my known contacts here. Okay. Thank you very much. And then wish you Happy New Year, everybody.
Thank you. It was really helpful to get feedbacks from you. So if you find anything that we can improve upon, kindly let us know in this conference so that next year, whatever mode it may be, we'll able to make it more better and better. So I must say that it's not only me, it's a full team. If you might see me in front, but my background is full of my students. So they are doing a great job for me. So starting from YouTube, so you'll be surprised to know that the first day conference was, just now I checked, it's more than 1,100 views for the first day YouTube link that we shared with all. So they are actually doing a very hard job for all of us. So it's like a family. So all my PhD students, those who have completed there, now many of them are my colleagues now. And from Australia, from Canada, they are still working quite hard to make this event as successful as possible. So now it's open. So anybody would you like? I cannot see many faces here because cameras are not on, so it's not popping up. So anybody from the audience, anybody would like to say something? Please share your views or anything that we can add up so that could be better meant for this conference. So anybody, Rupen, are you here?
Yes, sir, I'm here.
Okay. So, like to say something?
Hello, sir. Yes, sir. So I'd like to congratulate the whole of sir, the organizers for giving me an opportunity to present my paper. It was a wonderful experience, in front of a huge gathering of such learned people. I learned a lot from this conference. Hopefully, I will join. I will be joining in the next session as well. Wishing everybody Happy New Year in advance and also Merry Christmas from my side. And thank you, sir. Thank you, the organizers, and to everyone.
So it's a IMBIC family. So we all are part of this family. So it's welcome to you all. And anybody else would you like to add something? Yeah, Lena wants to say something. You are muted. Could you please unmute yourself? Lena, we cannot hear you. Could you unmute yourself?
I would like you to give my best wishes to your mother and all your family.
Yes. Okay, anybody else would you like to say something? Yes, only one, please.
May I?
Yeah, please.
Yeah. I'm Anirban Roy. I'm from Bangalore, Christ University. I just want to express my heartfelt gratitude. This is a wonderful experience to see so many mathematical stalwarts in one place. I was from that last 2 days. I have been thinking only. I wish it could have been a physical conference and meet and take photos with all of them because it's a lifetime achievement kind of things. And my special thanks to Professor Abhishek Adhikari because continuing this kind of legacy is not a simple thing. So wherever your father is there, he will be definitely very, very happy and satisfied to see you, sir. I mean, it's a learning experience, not only in terms of mathematics or others, in terms of the value systems of our India. So really, I salute you, sir. It's a very great thing you have done. And definitely you have been doing. In fact, I can help anyway. I will be the first person to join you because it's a great things what you have been doing. So thank you very much. And all my regards to all the professors here. And wish you all a very happy New Year 2022. Thank you.
Thank you. So it's not just as a team, it work really hard. We all work really hard. So you can see one of my students, he is now going back from university to back home on the train. So I requested him to be there if possible. So other students, many students are with me here. So he is one of my students who is working from home today. So making it like, you can see many accounts on my name, various persons all over the world now. My students are now helping me out for doing these things as an admin. So it's on YouTube, starting from YouTube to joining people and making it a time. So we have a very good coordination over WhatsApp. So we are thankful to WhatsApp as well as Google too for giving a smooth running of this kind of event. Okay, so anybody else would like to say something? Okay, so if not, then I wish you all the best, very best. And it's because of you, we get all the energy so that we can accommodate people and we can meet people, we can talk with each other. it is really a great experience. Day by day, we are learning things. And I hope that in the next year also, we'll able to make it in a physical mode. And we'll be in a more better shape to present you. And the quality as well as the presentation quality as well as the things will also increase. And yes, really, we all miss the food that we usually have during our lunchtime. It's really those who have be there in previous past events, they might have experienced that. We really missed it. So most importantly that I miss very much is my father. So with that, thank you all. See you next year.
Thank you.
Thank you. Happy holidays to all of you.
Thank you.
Thank you. Bye.
Thank you, sir. Thank you, all of you, sir.
Bye.
Thank you, sir.
So Lena, is there any plan for your birthday today?
Pardon?
Any plan for your birthday celebration?
Yes, I'm just expecting my grandchildren, but they are a bit late. They were going to be here now, but there is a lot of snowing, so it might be they are late, but I wish they would come and you just say hello, but they are not, I can't hear anything, they are late. Sorry.
Yes, it would be nice.
Yes, thank you. Jag tänkte om barnen kom, men det går inte.
Jag tänkte samma sak.
Ja, men då så tar vi väl och...
Okay, so that's great. Thank you. So from India, it's good night and see you in the next year. Okay, bye.